Okay, now I'm going to introduce the idea of a differential operator as a way to solve a system of differential equations. Okay, recall that if y is a function of t, y prime of t means dy dt. Now we can think of that as an operator, the derivative, applied to the function y. So you could write it this way: the derivative with respect to t of the function y. Okay, now that's emphasizing that it's the derivative of a function y. Now, often they'll use the symbol d to represent that operator. So d, the derivative with respect to t, is d of y. Okay? Now, if we're talking about the second derivative, recall that the second derivative just means you're taking the derivative of the first derivative. So if dy dt is just the derivative with respect to derivative of y, using this differential operator notation, this will just be applying the derivative again to the derivative of y. Now, we'll write this, you could write it as d dy, where you look at it as a product here of the two derivatives, but it's actually a composition. So it's the derivative of y, and just for convenience sake, we're going to write this as d squared y. Okay, so now let's look at an equation and see how would we convert it to the differential operator notation. So we've got a differential equation here. We know that the y double prime, the second derivative, is equivalent to d squared of y. Okay, so that's like that second derivative applied to the function y, plus 4 times y prime. Well, y prime is just the derivative applied to the function y. Remember, that's like d of y. And then plus 3 times the variable y. So we've got d squared y plus 4dy plus 3y. Since all of those are applied to the function y, we can write this as just a single operator, d squared plus 4d plus 3 of the function y equal to 0. Okay, so that operator is this is the operator applied to the function y. Okay, so just remember, when you see products, those are really compositions. So if we had something like the one I just showed you, d dy, that's the same thing as d of y. Or if we'd had something more complicated, d plus 1 as an operator times a d plus 3 of y. This is the operator being applied to the function y, but this is equivalent to taking the operator d plus 1 and applying it to d plus 3 applied to y. Okay, you don't have to put the parentheses around the y, just to emphasize the composition here. Okay, and so this would be the derivative of y plus 3 times y. And then you could apply the operator d plus 1 to that. Okay, so now let's look at various forms of the operator. So if I have d plus 1, d plus 3, that's the operator that's acting on some function y. I want to show that it's the same thing as what I'd get if I applied this operator, d squared plus 4d plus 3, to the function y. So d plus 1 times d plus 3 of y, remember that's just a composition, that's d plus 1 times d plus 3 applied to the function y. Well, applying d plus 3 to y, I'll have the derivative of y plus 3 times y. Now, the derivative of y here is just y prime. Okay, now, we've got an operator applied to this function. I'm going to take the derivative of the function, so that's the derivative of y squared plus 3y plus 1 times y prime plus 3y, prime, not squared. Okay, so now this is the derivative of y prime, which is the second derivative. So I could write it this way, derivative of y prime, and then plus 3 times the derivative of y, plus 1 times y prime, plus 3 times y. Now, the derivative of y prime, though, is just y double prime. And I've got this dy here, which is just y prime. So this y prime and 1 y prime, I have 4y prime plus 3y. Okay, now recall that y double prime, so this was y double prime plus 4y prime plus 3y. Y double prime is equivalent to the second derivative of y. Y prime is equivalent to 4 times the derivative of y, and then plus 3y. And we can write that as the operator d squared plus 4d plus 3 all applied to the function y. And so that would be equivalent, this operator is equivalent to this operator. When they're applied to y, they result in the same thing. Okay, now let's look at this. D plus 3t applied to d is not the same as d applied to d plus 3t. Now notice we're switching the order of the multiplication here. This first one means that we're trying to see how this operator applies to the variable y. So d plus 3t applied to y is the same thing as d plus 3t applied to dy. Remember, think of the product as a composition. And that just means that here's y prime. So now that's the function that d plus 3t is applied to. That's the derivative of y prime, which we know is y double prime, plus 3t times y prime. Okay, so now let's see, what does this look like when it's applied to the function y? Well, this is the same thing as the derivative of this first operator applied to y. And inside we have the derivative of y, which we know is y prime, plus 3ty. Now we want the derivative of that. Well, the derivative of y prime is y double prime. The derivative of 3ty, remember this derivative, this operator, was actually the derivative with respect to t. So when we look at this function, we actually have a product. We have a t here, and we have a function of t here. So using implicit differentiation, this is equivalent to the derivative of 3t, which is 3, times the y, plus the 3t times the derivative of y. So this is just using the product rule. Since the d is the operator, we're taking the derivative with respect to t. Okay, and now you can see that this is not the same expression as this. We have this extra term in here. So when you have something other than a constant with these operators, when they're added like this, you won't work with them the same way. You won't have equivalent expressions just by switching the order of multiplication, whereas up here, d plus 3 times d plus 1 would have yielded the same exact thing as this. So just be careful when you're dealing with these operators. We can only deal with constants that are added to those differential operators and get equivalent expressions. Okay, because the algebra of differential operators follows the same rules as the algebra of polynomials, we're going to use the elimination method to solve algebraic systems of linear differential equations that have constant coefficients. So to do that, we're going to first rewrite the equations in differential operator notation. Now, I'm going to collect the terms that have the same variable. So I see here that x prime, which would just be the derivative of x, is equal to 3x minus 4y plus 1. I'm not going to use the x of t or y of t. X and y are both functions of t here. Okay? And x and y are both dependent variables, with y being the independent variable. Okay, now this is the differential operator notation. To use elimination, though, I want to collect the common variables. So I'm going to take this dx minus 3x and rewrite that as just a differential operator d minus 3 of x. Okay, so this first equation then becomes d minus 3 of x plus 4y equal to 1. The second equation, I want to combine my two y's. This will be d of y. I'm going to bring this over, so I'm going to have a d plus 7 of y, and then I'll take this 4x to the other side. That'll be a minus 4x Notice I'm lining my x's up here and I'm lining my y's up so that I can do elimination. Okay, now let's start by eliminating the x. To do that, I need the coefficient of x to be the same for both equations. So I'm going to take the first equation and multiply both sides by minus 4. Then I'm going to take the second equation, not minus 4, positive 4, because I already have the minus in the bottom. The second equation, I'm going to apply the operator d minus 3 to both sides. So it would be d minus 3 of 10t when I get there. Okay, so now let's simplify the two equations a little bit. I've got 4 times d minus 3x plus 16y equal to 4. The second equation becomes minus 4d minus 3x plus d minus 3 of d plus 7 of y equal the derivative. D minus 3 of 10t means the derivative of 10t, which will be 10 minus 3 times 10t. Okay, so now let's just add the two equations. When I add them, the x's are going to go away. I'm going to get d minus 3 times d plus 7 plus the 16, all of that, of y, equal to 14 minus 30t. Now cleaning this up a little bit, this becomes d squared plus 4d minus 21 plus 16 will be minus 5. Okay, so now what we have is we have a non-homogeneous second order linear differential equation. Remember, this is just, if you wanted to rewrite it, this is the second derivative of y, so that would be like y double prime plus 4, the derivative of y, minus 5y, and then equal to the 14 minus 30t. So now, the first step to solving this non-homogeneous equation would be to solve the homogeneous equation. Now you can look here to get your auxiliary equation, or it's actually simpler if you just look at the differential operator here. If I factor that differential operator, I'm going to have d plus 5 times d minus 1 of y equal to 0. So that's the homogeneous equation, and it automatically has the solutions, the roots to the auxiliary equation by looking at these two factors. So I know that the auxiliary equation would be the m plus 5 times m minus 1 equal to 0. So m is negative 5 and m is 1. So that my solution to the homogeneous equation is y equal a constant e to the minus 5t plus a constant e to the t. Okay, so that's the complementary solution. Now we need to find the particular solution that gives us the 14 minus 30t. So based on that form and looking at the complementary solution to make sure there's no overlap, we're going to guess that the particular solution is of the form a times the t plus a constant b. So now that means that y prime would be a and y double prime would be 0. So plugging those into this differential equation, so I've got this on the left equal to this on the right. I'm going to have 0 plus 4 times y prime minus 5 times the y, and that has to equal to 14 minus 30t. So we've got 4a, our constant terms will be 4a minus 5b, and that has to equal to 14. And then we've got minus 5a times the t here have to equal the minus 30. Okay, so that's the t terms. Okay, that tells me that a is equal to 6. And then filling in a equals 6 up here, we've got 24 minus 5b equal to 14. So that means minus 5b is negative 10. So b is equal to 2. So our particular solution would be 6t plus 2. And so our solution for y would be y equal c1 e to the minus 5t plus c2 e to the t plus 6t plus 2. So we've got our function y of t. Be sure you use t's on the right side. Now we need to go back and find the function x. Remember, we had two functions we're looking at here. We're looking for x of t and we're looking for y of t. Okay, now we have two choices to get the x. We can go back up to this original equation here and now eliminate the y to find x, and then I'll show you another way besides that. So let me get rid of some of this work so I can use the same slide here to solve it. In fact, I'm going to get rid of all of it. You can always replay it. Okay, so we had 1 and 4t. 10t. Okay, so there's our equation, our system. Now we want to eliminate the y. Okay, to eliminate y, I'm going to multiply the second equation through by negative 4. And the top one, I'm going to apply the operator d plus 7 to both sides. Okay. Okay, so eliminating the y, we're going to get, we'll have d plus 7 applied to d minus 3x plus d plus 7, let's see, times the 4, I'm going to put the 4 first. And now the derivative, d plus 7 of 1 means the derivative of 1 plus 7 times 1. Well, the derivative of 1 is 0, and then 7 times 1 is just 7. For the second equation, we're going to have 16x minus 4d plus 7 equal negative 40t. Okay, so now add in the equations. The y's will eliminate. We're going to get d plus 7, d minus 3 plus 16, all of x. Okay, this simplifies to be d squared plus 4d minus 5 of x Okay, looking at the homogeneous equation, you would be solving for the second derivative of x plus 4d, the derivative of x, minus 5 times x equal to 0. We can use this, which would be our auxiliary equation with if we put m's in there. So the m values, because since this is just d plus 5 and d minus 1, the m values would be minus 5 and 1 again. So our x then, since that was the differential equation was in x, is going to be some constant. Now I can't use the same constant, so I'm just going to call it k1 e to the minus 5t plus k2 e to the t. That's the complementary solution. Now we need to deal with this 70 minus 40t. And again, our particular solution would be of the form a times t plus b. Applying it to this differential equation, the second derivative of x would just be 0. Well, this is x of p, I'm sorry. Particular solution for x. Okay, so the second derivative of x is 0 plus 4 times the derivative of x, which would be a, minus 5 times the x must be 7 minus 40t. Okay, our constant term is 4a minus 5b, and that has to be 7. And then minus 5a is the coefficient of the t term on the left, and minus 40 is the coefficient on the right. So we know then that a is 8. Plugging that into the first one, we get 32 minus 5b is 7. So that means that minus 5b is negative 25, so b is equal to 5. So we have that the particular solution x of p is 8t plus 5. So our x is k1 e to the minus 5t plus k2 e to the t plus 8t plus 5. Okay, now the problem with that is we now have a system where we have 4 constants, the c1, c2, k1, k2, but each of these x prime and y prime were just first order. So normally when we have a first order differential equation, we only end up with 1 constant. So having 2 different variables, though, first order, we should end up with only 2 constants. So we need to figure out the relationship between the c1, c2 and the k1, k2, because we should have 2 constants among the 2 equations. So let's see if we can go back and find their values relative to each other. So again, I'm going to erase this so I can see my original equations. I'm going to plug both of these in to the original equations. And just pick whichever one you think is easiest to work with. I'm just going to use the top one. Okay, it says that x prime, so I've got to take the derivative of this function. X prime would be minus 5 k1 e to the minus 5t, I'm just taking the derivative of x down here, plus k2 e to the t plus 8t plus 5. I want the derivative of x prime. I take the derivative of everything. So I took the derivative of this first term, took the derivative of the second term, need to take the derivative of this, so it'll be just 8, and then derivative of 5 is 0. That has to equal to 3 times the x, so that's 3k1 e to the minus 5t plus 3k2 e to the t plus 24t plus 15. So I did 3 times this entire equation here, 3 times the x, and then minus 4 times the y, so I'm going to have minus 4c1 e to the minus kt minus 4c2 e to the t minus 24t minus 8. I just did minus 4 times this entire equation here, and that's where this came from. And then we have plus 1. Okay, so if I want to highlight this, this was this, and this was this. So I'm just plugging these 2 solutions into the first equation. And it has to be true if those are solutions to the equation. So let's see if we can combine some terms and compare them. I've got minus 5k1 e to the minus 5t plus k2 e to the t plus 8. On the right side, combining the e to the minus 5t terms, I'm going to have 3k1 minus 4c1, that's e to the minus 5t. And then I'm going to have a 3k2 minus 4c2 e to the t. The 24t and the minus 24t cancel, and I've got plus 15 minus 7, which is plus 8, which is good because now that will cancel. Okay, so now for these 2 equations to be equal, minus 5k1 has to be equal to this. And the k2 here has to be equal to 3k2 minus 4c2 over here, the coefficients of the e to the t. Okay, so that gives me that, I'm just going to put the 4c1 on the left side, and I'll have 8k1 on the right side. And then the second one here, I'm going to have 4c2 equal to 2k2. Now, it doesn't matter which one you solve for. Solve for either the c1, c2, or the k1, k2. So just for simplicity, not having to deal with fractions, I see here that c1 is equal to twice k1. And solve for the same variable c. c2 is equal to 1/2 k2. Okay, so if I'm doing that, then I'm going to keep my second equation that has the k's in it for the x. So I'm going to have that x is equal to k1 e to the minus 5t plus k2 e to the t plus 8t plus 5. And then my y is the c1, which is twice k1 e to the minus 5t, plus the c2, which is 1/2 of k2 e to the t, plus 6t plus 2. And there's your two equations. We have just two variables now, the k1 and the k2. Now, you could have just as easily have solved for k1 and k2 here and substituted those into the second one and had all the equations in terms of c1 and c2. So you may not get the same answer, just make sure you have the two equations in terms of the same constants. Now, that was a pretty tedious process because we first eliminated the x and solved for the equation for y. Then we went back and repeated the whole process. There might have been a simpler way if we solved for the correct one first. Now, if you can go back and look at the original equations and be able to solve for either the x in terms of just the y variables, like this first one, I could solve for the x and get it in terms, well, I can't solve for the x in that one because I've got an x prime also. The second one, though, I could have solved for x and gotten it in terms of just the variable y. So the second one here, I could have said, well, that means that if I take all this to the other side, that means I'll have y prime plus 7y minus 10t will equal to 4x. So if I take 1/4 of this, then I'll get what the x function is. So that means if I had solved for y first, I can get x just by using the y to get it. Or, notice the first one. I could have taken this one and solved for the y. This tells me that x prime minus 3x minus 1 will equal to negative 4y. And then if I just multiply this by minus 1/4, I would get what the y was going to be. Okay, so you can get y then in terms of the x by just using that first equation. So let's try that, and we'll see if we get these same answers. So it assumes that you found one of them first. So since we did the x first, let's assume that we found the x first to be this. And now we're going to go back and figure out what the y is. So let me get rid of all this work so we can look at it compared to this. So what you have to do is you have to look at the original equations first to figure out which one would be best to solve for first, so you'd eliminate the other one. So can I solve for y and get it only in terms of x's? No y prime also, and you can. The first one here, you can solve for y and have it just in terms of the x's. So I'm going to take this first equation again and say, okay, this would be x prime minus 3x minus 1 equal to negative 4y. So my y will be negative 1/4 x prime minus 3x minus 1. Okay, and again, we're assuming this is our x. X prime will be minus 5k1 e to the minus 5t plus k2 e to the t. I'm taking x prime here, plus, and remember, we're taking the derivative with respect to t, so plus 8 plus 0, and now minus 3 times the x, that'll be minus 3k1 e to the minus 5t minus 3k2 e to the t minus 24t minus 15. So this is all the 3 times the x here, and then minus 1. Add the e to the minus 5t terms. Add the e to the t terms. The constant. So we have 8 minus 16 will be minus 8. So our y will be 2k1 e to the minus 5t plus 1/2 k2 e to the t plus 2. My 6. Oh, I left this off. And it matches exactly. So this will be a lot less work if solve for one of them and then get the second one by using the original equations and solving it in terms of the previous one that you found. So again, you could have, if you solve for x first, then you can use this to get the y. Or if you'd solve for y first, then you would have already had this and you could have solved for the x. But check first, because you can't always do either one. Sometimes you have to do a certain one first and then get the other one. Okay, so let's just review what we're doing here. If you want to find a general solution of a system here, okay, I've already got it in terms of the differential operators. Okay, so we're assuming that these are differential operators. They'll use the notation L to represent those polynomials. So the L might have been a D plus 3 or D minus 1. So you've got this system in terms of the differential operators D. Okay, so first, make sure the system's written in operator form. Second, eliminate one of the variables, for instance, the y, and solve for the other variable. So you'd solve for, if you eliminate the y, you're going to solve for the x. Now you might have to solve both a homogeneous and a non-homogeneous equation to do that. Depends on what's on the right side. Okay, now once you've solved for that one, if possible, use the system to get an equation that involves just the y, okay, but not its derivatives. Okay, so we've already solved for x. Now we need to solve for y. So can you get y equal in terms of just the other variable, the x and the x prime? Okay, and if you can, then use the original equations and what you already found here for the x to get the y. If you can't, then you'll go down and eliminate the x and find the y, but then you have to get your variables to be related. So if you can't solve for one of them in terms of the other one there, you're going to eliminate the x from the system and solve for the y. And then you've got to remove the extra constants by plugging both of them into one of the equations and figure out what the related constants are. Okay? So that's your method. Okay, let's look at some other examples. first step, we have a system here. These are second order linear differential equations. I do notice the first one has a second order derivative of x, but not of y. But could I solve for x or y from either of those two equations in terms of the other one? If I tried to solve for x here, I would have this x double prime. If I tried to solve for y here, I would have this other y prime. So I'm not going to be able to do that with the first equation. The second equation, if I try to solve for the x, I'm going to have I have another x prime in there. And if I try to solve for the y, I can solve for y prime, but I can't solve for just y. Okay, so neither equation can be solved for x or y just in terms of the other variable. But notice something that we can do. Because of these, there's not that many y's in the equations, and the first equation and the last equation both have the same exact number of y prime. So if I took the first equation minus the second equation, I would get x double prime minus x prime. The y primes would eliminate. The x of t's would eliminate. And then plus the y of t equal negative 1 minus t squared. I now have an equation that I could solve for y if I knew what x was to begin with. So what I want to do first is I want to solve for x first. So that means I'm going to eliminate the y. Okay, so let's start by setting our equations up in differential operator notation. So I'm going to have d squared x plus dy minus x plus y equal negative 1, which that becomes a d squared minus 1 of x, take the x out of each, plus a d plus 1 y equal negative 1. There's our first equation. The second one, this would be a dx plus a dy minus x equal to t squared. So I would have a d minus 1x plus a dy equal to t squared. Okay, so here's our equations in the differential operator notation. And notice that first one, if we factor that d squared minus 1 as d plus 1 d minus 1, which will be an equivalent differential operator, I'm just rewriting the first one. Then I can easily see how, but I'm wanting to eliminate the y first, not the x. So to eliminate the y, I'm going to multiply the top one through by minus d, and the bottom one through by d plus 1. I found eliminating the y first will give me the x, and then I can easily get the y from it. So the y will be equal to, well, I'll solve for that later. Okay, so this system becomes d plus 1 applied to t squared. That's the derivative of t squared, which will be 2t plus 1 times t squared. So be really careful when you're applying derivatives. Whoops, I just multiplied these over here, and I didn't do that correctly either. I'm taking negative 1 times the derivative of negative 1. Erase it. So the derivative of negative 1 is 0. Now add the two equations. The y's will eliminate here. So we're going to have, now notice I have this whole thing, the d plus 1, d minus 1 is in common. And then I'll have a minus d plus 1, so 1 minus d of x. So just adding these two together, I'm factoring out the d plus 1, d minus 1. Okay, which this is just minus d minus 1. So I've got minus d minus 1 squared d plus 1 of x. And if I don't want to deal with this minus, I could distribute it on the right side, but I'll just leave it there. Well, obviously I'm not. I'm changing it. Okay, so looking at the homogeneous equation. The homogeneous equation would be this equal to 0, and so x, which is the variable that we're looking at, x sub c would be equal to some constant e to the t. Since we have a duplicate root here, a double root, we're going to have a constant t e to the t. And then my second one is constant e to the minus t. Okay, so your roots were 1 twice and then negative 1. So that's the complementary solution. The particular solution based on this form would be power of t squared. Power of t and then another constant. And there is no overlap between those. So looking at this equation, it's a little harder to see what we're doing there. I need to apply that operator. So let me go ahead and expand this thing out. So I have the d minus 1 squared times the d plus 1x, and that has to be minus 2t minus t squared. So distributing this through, we're going to have d cubed. I'll have a plus d squared minus 2d squared minus a 2d plus d plus 1. Okay, so that's the third derivative of x minus the second derivative of x minus the derivative of x plus 1. Okay, so now let's look at our particular solution down here. X prime is 2at plus b, and x particular solution second derivative would be just 2a. So now the third derivative, we need it, is just 2. So this is the third derivative of x, which would be 2, minus the second derivative of x, which will be 2a, minus the derivative of x, so minus 2at minus b, that's the minus here, and then plus 1 times x, and that needs to come out to be minus 2t minus t squared. Okay, let's take our t squared terms. We know that a has to be negative 1. Our t coefficients, we know that minus 2a plus b has to be negative 2. So since a is negative 1, that means that 2 plus b is negative 2, so b is negative 4. And our constant terms will be 2 minus 2a minus b plus c. And they should be 0, because there's no constant term over here. So c is negative 8. Okay, so that means our particular solution for x is negative t squared minus 4t minus 8. Okay, so our equation for x then, and I'm just going to put it up here. Okay, before I go any further, let me correct one little mistake here before I get a bunch of emails about it. This is a constant. The variable was t. So x triple prime should have been 0. And so here we would have had a 0, which the only place that affects it is here, which is going to cause this to come out to be negative 6. So I just want to correct that before we get too far into this. Okay, now we're good. Okay, now let's go back and find the y. So again, we could come back here, eliminate the x's and solve for y, but then we're going to plug them both into one of the equations and get more, constants and have to go back and figure out what they are. So that's going to be a long, tedious process. But we noted that had we added these two equations or subtracted them, we'd have this minus this minus this, the y primes go away, this minus this, the x's go away, minus plus this, and then this minus this. We ended up with this, which could easily be solved for y just in terms of the x. So I'm going to get rid of all this, and we're just going to solve for the y now in terms of the x. So we're going to have, based on this, which was just a combination of these two equations, the first one minus the second one, we get that y is going to be equal to minus the second derivative of x plus the first derivative of x minus 1 minus t squared. I just solved this for the y. Okay, so now y will be equal to minus the second derivative. So let's find some derivatives of this thing. So if that's the first derivative, let me just go and write it this way. Minus, here's going to be the second derivative, plus the first derivative. I'm going to put x prime in here now. X prime will be c1 e to the t. Ooh, I need the product rule here. It will be c2 e to the t plus c2t e to the t. So that's the product rule for the derivative of this thing. Minus c3 e to the minus t. I'm taking the derivative. Minus 2t minus 4, and then a constant. So this whole thing here is my x prime. So I think I'm going to need a little more room for my second derivative. Okay, so the second derivative will be the derivative of that thing, the thing that's in the parentheses. And let's see, before I do that, I can combine a couple terms. This is c1 plus c2 e to the t, which they don't really combine that nicely though. Okay, so my y, I'm just trying to save time, not having to write that thing down twice. I want the x double prime here. So this is x prime. X double prime then will be c1 e to the t plus c2 e to the t plus, again, the product rule here will be c2 e to the t plus c2t e to the t plus c3 e to the minus t and then minus 2. Okay, I'll fit it. Okay, so this is x double prime. And then we need to put the rest of this. So we have minus x double prime plus x prime minus 1 minus t squared to all of that. And so that'll be my y when I get it. Okay, so I've got negative c1 e to the t minus c2 e to the t minus c2 e to the t minus c2, I'm just distributing this negative 1 times everything in here, t e to the t minus c3 e to the minus t plus 2 plus c1 e to the t plus c2 e to the t Okay, now simplifying. I want to combine all the e to the t. So that's this one, this one, this one, this one, this one, just the plain e to the t. So I've got minus c1, minus c2, minus c2, plus c1. So this one and this one cancel. This one and this one cancel. So we get just a minus c2 e to the minus e to the positive t. Now I want to look at the e to the minus t terms. So that would be this one and this one. So that looks like a minus 2c3 e to the minus t. And I want to look at the t e to the t terms. One here and one here. So that's going to be, well, those cancel. Okay, and then we have a minus t squared, a minus 2t, and then a minus 5 plus 2 is a minus 3. Okay, so we've been working with equations that had constant coefficients. If you have an equation that has variable coefficients, there's a very limited number of methods to solve those. Now, we can write the solutions using an infinite series, but we'll see that that's a very tedious process to do so. Okay, the one case that has variable coefficients that we can easily solve is called the Cauchy-Euler equation, and it has very special coefficients so that you'll have like an x squared in front of the second derivative, an x in front of the first derivative, and then your y value. So that would be the Cauchy-Euler equation. Okay. Fortunately, all other cases where you have, whether you have constant or variable coefficients, linear, nonlinear, or even higher order equations, they can all be solved using numerical processes, including a system of the differential equations. So numerical processing is the way most of these equations will be solved. Okay, so what we want to do is we want to be able to express differential equations as a system in normal form. And then we're going to use our basic Euler method in the computer to vectorize the solutions to apply to those systems. Okay, so remember, normal form is where you have the derivative. So y prime was equal to a function of the independent variable, t, x, whatever it was, and then the variable, the dependent variable as well. So this was the normal form that we discussed previously. Okay, so just defining a system as normal form, we have a system of m differential equations, okay, with m unknown functions, x1, x2, x3 up to xn, and we're going to express that system. Now this is a system where each of the first derivatives is in normal form. So we have x1 prime is a function of t in all those dependent unknown functions. x2 prime is a function of the independent variable and all those other unknown functions, and so on up to the x sub m prime. So this is a system that's in normal form, and it has m different differential equations. Now, in vector form, we would just say that x prime, so the vector x prime is x1 prime, x2 prime, down to xm prime, or we could just say that it's the vector x, which would be x1 to x2 down to xm. So if this is the vector x, we're going to take the derivative of that. And we're taking the derivative of that with respect to the independent variable t. Okay, so this is how you would write it in vector form, where you just write a single equation just representing the vector x, which is the vector that contains each of those dependent variables, dependent functions, and then x prime would just be the vector that contained the derivatives of each one of those functions. So that's a way to work with it easily, as one entity in the computer. Okay, so a single higher order equation can be converted to an equivalent system. And that system will be first order equations. Okay? So we might start with an nth order differential equation like this, so that the variables involved would be the independent variable t and all the derivatives, y prime up to the m minus first order. Okay, so what we want to do is to write that as a system that has m equations, okay, and that each one is a first order equation. Okay, and the way we're going to do that is to define a sequence of functions. We're going to let x1 be just the y function. We're going to let x2 be the derivative, and we're going to go up to xm would be the m minus first order derivative. Okay, so if x1 is yt, that means x1 prime will be y prime. That means x2 prime will be y double prime, but this y prime over here was actually x2. Okay? So we have that x1 prime is y prime, but that's also the x2. Okay? We have x2 prime is y double prime, but that's also x3. Okay? So there's your second equation. And you'll continue doing that up till the x of m minus 1 prime, which I don't have that written here. So x of m minus 1 would have been the m minus 2th order derivative of y. Okay, so if we take x of m minus 1 prime, that means we're taking the derivative of the m minus 2 or the derivative of y, which will just be the m minus 1 ordered derivative, okay, which will be just x of m. Okay, so we have this equation. So now our final one will be the x of m. We know that the x of m is the m minus first order derivative, so that means x of m prime will be the mth order derivative of y. Okay, so we have x of m prime is the mth order derivative of y, but that was the original problem. So here's our original function. Okay, so we've got this system now, but they're all first order equations, but if this, what satisfies those will satisfy the original differential equation. Now, one thing nice about this is it also, is easy to convert an initial value problem, because let's say that we're given the conditions that y of 0 is equal to some constant a, and y1 or y prime of 0 would be maybe some b, and so on. I guess I should have used subscripts. Okay, and we'll have up to the m minus first order derivative if we have a system of m equations, and that would be a sub m minus 2. Okay, so now if y of 0 is a, and we've just converted the original differential equation to one that contains these x's are the unknowns that we're looking for, then if y of 0 is equal to a, y is the same thing as x1. This just means that x1 of 0 is a1. Now y prime is x2. So this just says that x2 of 0 is a2. Y double prime then would be x3. So this would just say x3 of 0 will be a3. Okay, so y to m minus 1 will just be xm of 0 equal to a m minus 2. And that doesn't look right. A sub m. Whatever the numbers come out to be. Okay, so let's demonstrate this on an example. Okay, so I want to convert the initial value problem into a system in normal form. Okay, so the way I'm going to do that is to define new variables. X1 will be equal to y. Okay, so that means my first equation, x1 prime, will be y prime. X2 is equal to y prime. So that means x2 prime will be y double prime. Okay, so now let's look at our initial problem here. Let's put it in normal form. In normal form, this would be y double prime equal sine of t minus 3t y prime plus y squared. Okay? So this second derivative here will be just sine of t minus 3t y prime plus y squared. Now notice that this is a function of the independent variable t, the y, and the y prime. Now our goal here is to get this to be a system of the independent variable t and each of the x's. Okay, so now let's go back. We have y prime. The y prime, though, is the same thing as x2. So this is equal to x2. So x1 prime is x2. Now the x2 prime, we have that it's y double prime, but we've already rewritten it here in terms of the original function in the variables. So this would be sine of t minus 3t. The y prime is the x2, and then the y is the x1. Okay, so one more step here. We've got the system now in normal form. We have x1 prime is x2. We have x2 prime, which is sine of t minus 3t x2 plus x1 squared. Okay, and now our conditions, if y evaluated at 0 is 1, that means x1 evaluated at 0 will be 1. And y prime is the same thing as x2, so we'll have that x2 of 0 is 5. So here's our system in normal form. It's a system of first order equations, and we've got the initial conditions. And the new variables now are the x1, the x2, and then our independent variable t. So we've just taken a second order differential equation and converted it over to a first order system. Back in chapter 4, we looked at second order linear differential equations. Now we're going to extend that to higher order linear differential equations. So recall a linear differential equation of order n is an equation that can be written in this form. If y is the dependent variable, you'll have the function y, you'll have derivatives of y up to the nth order derivative, but everything else, any of the coefficients of those derivatives or the coefficients of the y itself can only be functions of x. Also, on the right side, that function can only be a function of x. So all of the a's in this depend only on x, not on y. When all of the coefficients, so if you take all these coefficients that are in front of the y's or the derivatives of y, when all of these are constants, we say that this equation has constant coefficients. Okay, so we'll say it's a linear equation with constant coefficients. If there's variables, if the variable x does appear in any of those, then we say it has variable coefficients. So we're going to have different methods to solve these equations when they have constant versus variable coefficients. Okay, so now if the b over here on the right side, if the function that doesn't have the y or any of the derivatives of y in it, if that function is 0, then we call this equation a homogeneous equation. If it isn't 0, then we call it a non-homogeneous equation. Okay, so now as we solve these, we're going to be assuming that all of these functions a and the b are all going to be continuous on some interval I, and since we're saying it's an nth order, the a sub n of x is not 0 on that interval as well. So we want to make sure that this leading coefficient is not 0. Okay, so If it's not, then we're going to be able to rewrite this equation in standard form. Okay, now the standard form then is going to be just dividing the entire equation by this a sub n term. Okay, and so here's our standard form. So all the functions then, the p1 all the way up to the pn, are all going to be continuous, as well as the g of x on that interval. So again, the interval I is an interval where we know that the a sub n of x is not 0. Okay, so now let's look at when we know there will be a solution and a unique solution to an initial value problem. Okay, so we're looking at that linear differential equation, nth order, in standard form. Okay, so here's our equation in standard form. So all the p's and the g are all continuous on some interval ab that contains some x naught. X naught is the point, the x value, where the initial condition is going to be given. Okay, so we have the y value at that x naught. Okay, and it'll be some gamma naught. The y prime at that x naught will be some gamma 1. So we're going to have the function's y value, the derivative at that x naught, up to the nth derivative, or n minus 1th derivative at that x naught as well. So that's the initial value problem. Okay, it says for any choice of the initial values, so it doesn't matter what values we choose for these, the y value, in all those derivatives, there will be a unique solution on the interval AB to this initial value problem. Now, keep in mind again that this was an interval where that leading coefficient of the nth derivative was not 0. Okay, and each of those functions, the p1 up to the pn and the g, all have to be continuous on that interval. Okay, so let's look at a problem and see if we can come up with the intervals where we have the guarantee of the existence of a unique solution. Okay, so start with the initial value problem. Here's our third order linear differential equation. Okay, so you see our third derivative here, second derivative, first derivative, and the y value. Notice the functions in front are all continuous functions and only functions of x, as well as the function over here is only a function of x. Now that function will only exist for x is greater than or equal to -5. Okay, so now our initial value problem is giving us the values at some x naught. We don't know that. We're looking for what intervals the x naught can be in that will make their guaranteed unique solution. Okay, so the first thing we have to look at is we have to look at the problem in standard form. So we'll rewrite the problem in standard form. So we have the an here cannot be 0. So any interval that we choose cannot have this a sub n of x equal to 0. So we know for sure that x cannot be equal to 0 and 1. So intervals cannot contain 0 and 1. Since we know that a sub n of 0 would be 0 and a sub n of 1 would be 0. Okay, so in standard form, this differential equation becomes y triple prime minus 3x over x times x minus 1, y double prime plus 6x squared over x times x minus 1, y prime minus cosine of x over x times x minus 1 times y equal the square root of x plus 5 over x times x minus 1. Now we want to find where all these functions, these are the p's, right? The p1 up to the pn and then the g. We want to find where those functions are continuous. This, 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 and this. So these functions will be continuous when x is not 0 x is not 1. And then this last one, we also have that x must be greater than or equal to -5. Okay, so if we're going to look at the number line, and we want to make sure that x is not 0, x is not 1, and x is bigger than or equal to -5, that means that we're restricted to these values, and these values. Okay, so we're looking for that open interval, AB. So the only candidates for that open interval then would be from -5 to 0, 0 to 1, and 1 to infinity. So as long as we choose an x0 value, that initial value where all the conditions are given, in those intervals, then we would have all of these functions continuous, and that guarantees us that we will have a unique solution to the initial value problem. So choose, so x0 could be an element of -5, 0, x0 can be an element of 0, 1, and x0 can be an element of 1 to infinity. And we can choose smaller intervals than that, like 1 to 2, 1 to 3, but these are the biggest intervals that we can choose and let x0 be any value in those intervals. Okay, so now let's look at that linear differential equation that is in the standard form. So we have the y triple prime plus the p1 times the y double prime. Let's see, I'm not using double, I'm using n. So the nth order, we have the p1 and then the n minus 1 order derivative. Okay, so this is our equation in standard form. Okay, now recall that differential operator when previously we represented the nth order derivative as dn. So the d is representing the derivative, and then the order is represented as a power on the d. Okay, so if we rewrite this nth order derivative, we can write it as dn. The n minus first order derivative is d to the n minus 1, all the way down to the first derivative would be just a single d, which would be the term in here. Okay, so we would have a d, just a single d here, and now we have just the piece of n, which is a constant term. Okay, so we're going to look at the differential operator that's represented by this expression, okay, and we'll call that L of y. So y is just representing our dependent variable there. Okay, and so in that differential operator notation, remember we can, instead of saying the nth derivative of y for the, for this notation up here, we could write it as dn with y following it. And so then you can write this, then the operator with the y following. Okay, so that's equivalent to the nth derivative of y, and then plus p1, the n minus first derivative of y, all the way down to the first derivative of y, and then pn times the variable y. So that's just how that notation is represented. So now that whole equation then could be written as the differential operator of x, so that's our independent variable, is just the function g of x, which is what the right side of that differential equation is. Okay, so now keep in mind too that this differential operator, remember it's representing the derivatives. Derivatives had the linearity property, which meant that if you wanted to find the derivative of a sum, So something like a function plus another function. Remember, that was the sum rule, told us that that was the derivative of f plus the derivative of the g. Okay? Also, when you took the derivative of a constant times a function, that was the same thing as the constant times the derivative of the function. Okay? So these two together make that derivative linear. Okay? So this linear operator then, which is a differential operator, is just a linear operator. Okay? So that means then if we took the L and had a sum of functions here, that would be equivalent to L of each of the functions added together. So there's just our sum rule. Okay? If you had L of a constant times a function, that's just going to be the constant times the L of the function, which is just our constant multiple rule. Okay? Now, that's going to be really important because let's say that we're told, so if y1, y2, up to ym are solutions to the homogeneous equation. Okay? So that means then we're looking now at L of y of x equal to 0. So here's our homogeneous equation as opposed to the non-homogeneous up here with the g of x. Okay, so if each of these is solutions to the homogeneous equation here, that means that L of y1 of x is equal to 0. L of y2 of x is equal to 0, all the way up to L of ym of x equal to 0. Okay? Now what I want to look at is I want to look at a linear combination of these y values, these solutions. So if I had some c1 of y1 plus c2 of y2 all the way up to cm of ym, and I wanted to find the linear operator of that linear combination, well, because of the linearity property, I know that L of a constant is the constant times the L of the function, and I know that the L of the sum will just be the sum of the L's. So this can be rewritten as C1 L of Y1 plus C2 L of Y2 plus Cm L of Ym. And all of that is a function of x equal to 0. Okay, but keep in mind that if these were solutions, so if these values were solutions to the homogeneous equation, we know that each one of these is 0. That means that this is 0, well, the L of y. This part is 0, this part is 0. All of these are going to be 0. So what happens then is that this whole thing is equal to 0. So what that means is if we have a list of solutions to the homogeneous equation, and we take any linear combination of those, so a constant times each of those functions, then that will also be a solution to the homogeneous equation. Okay? So what we're going to hope to do then is we're going to hope to be able to find n solutions to the homogeneous equation. Okay? Not just n solutions, but we want those n solutions to have a special property that we're about to get into. If we find n solutions to the homogeneous equation with a special property, okay, and that's going to be called a linear independence property, then we will have all possible solutions. Then all solutions will be of the form C1y1 plus up to Cn yn. Okay? So that'll be all solutions to the homogeneous equation. So that's what we want to get to next, is actually finding the set of functions that are solutions that have this linear independence property. That will then lead us to having all possible solutions to that equation. And keep in mind, this was an nth order, so we're looking for that set of n linearly independent solutions. Okay, now we want to find the general solution of a homogeneous linear nth order differential equation with constant coefficients. Okay, so it's going to be an equation in this form, and we know that if it has constant coefficients, that a solution of the equation is e to the rx as long as r is a root to the auxiliary equation. Remember, the auxiliary equation we got from plugging in y equal e to the rx. Okay, we did it back when we were working with second order. Let's go ahead and repeat the process just to remind you for an nth order. So if y is e to the rx, then y prime will be r e to the rx, y double prime r squared e to the rx, and the nth derivative will be r to the nth e to the rx. So substituting those things into the derivatives here in the function, we're going to get an times r to the nth e to the rx plus an minus 1 r to the n minus 1 e to the rx. We're going to get down to a1 r e to the rx plus a0 e to the rx equal to 0. Now you notice that e to the rx is a factor of each of those terms, so we can factor that out. We're going to have an r to the n plus an minus 1 r to the n minus 1 plus all the way down to a1 r plus a0 equal to 0. Now recall that e to the rx can never be 0, so the only way that this product will be 0 is if this expression is 0. And that's our auxiliary equation. So if we can find the roots to this auxiliary equation, we'll know that the solutions will be of the form e to the rx, where r is a root to that auxiliary equation. So we also call it the characteristic equation. Okay, so let's look at different cases. We're going to start by looking at the roots of that auxiliary equation being distinct real roots. Okay, so let's say that we have r1, r2 up to rn are distinct real roots to the auxiliary equation. Then that means that our solutions will be e to the r1x, e to the r2x, e to the rnx, and for those n values. So we know that the general solution to the homogeneous equation then will be of the form y equals c1 e to the r1x plus c2 e to the r2x dot 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 cn e to the rnx. Okay, so we just need to find what those roots to the auxiliary equation are. Okay, so we want the general solution to this linear third order homogeneous, 0 over here, equation. And because it's constant coefficients, that's really important here, constant coefficients tells us that the form of the solutions will be e to the rx. Okay, so we know that since the solutions will be of the form e to the rx, then we know that our auxiliary equation will be r cubed minus 2r squared minus 5r plus 6 equal to 0. And we just want to find the roots to that. Now, there's not a solver that, nice formula that will tell us the roots to a degree third or higher polynomial. We have the quadratic formula for when it's degree 2, but if it's larger, you're going to have to come up with other ways. Now, in college algebra, you found ways to find the roots, the rational roots. And you looked at factors of this last term divided by factors of the leading coefficient. So the ones that are possible candidates, if they're rational roots, will be 1, 2, 3, and 6, or plus or minus of each of those. Now, we're going to have pretty basic ones in this textbook, so you're not going to have to look too far to find them. So remember that once you find one root, you're going to be able to get the others. I'm going to go ahead and show you synthetic division, because once you find one root, it automatically gives you the two factors. So let's say that r equal 1 is the candidate for what we want to see is a root for this equation. So I'm going to put 1 on the outside, and I'm going to take the coefficients of this auxiliary equation, 1, -2, -5, 6. Bring down the first term, multiply these two, and then add. Again, multiply these two, and then add. Multiply again, and then add. Now, if you come up with 0, that means the remainder was 0, which is good. That means that 1 was a root, so that means r minus 1 is a factor, and I have the other factor right here. It's r squared minus r minus 6. Always start at 1 degree less than what the original problem. So if it was an r cubed, this is going to start with an r squared. And now we could go ahead and continue to factor this. It'll just be r minus 3 and r plus 2. So that's just back, simple FOIL factorization. Okay, so our roots then will be 1, 3, and -2. Okay, so we do have real distinct roots. So that means our general solution will be y equal c1 e to the x plus c2 e to the 3x plus c3 e to the minus 2x. Remember, they're of the form e to the root times x. Okay, now let's look at complex roots. Okay, now when you have one complex root like alpha plus I beta, the complex conjugate's automatically also a root. So we know that alpha minus I beta will also be a root. Okay, now the complex valued solutions would then be e to the alpha plus beta I x and e to the alpha minus beta I x. So just putting those roots up times x in the exponent. Now, if we just want the real valued solutions, though, remember previously, we would take the e to the alpha x, so take the real part of that root, and it's e to the alpha x, and then cosine of the beta, take the imaginary part, and it's cosine of beta x. And then you're going to have e to the alpha x sine of beta x as well. So those are the two real valued solutions when we have the complex roots, alpha plus or minus beta I, for roots of that auxiliary equation. Okay, so now let's look at a general solution. We've got a third degree polynomial, and again, we know that the form of the solutions, because this is a linear, third order, homogeneous, and the critical part here is constant coefficients. That's what tells us it's y equal e to the rx for the roots. Okay, so getting the auxiliary equation, we have r cubed plus r squared plus 3r minus 5 equal to 0. Okay, well, we know the possible rational roots to this will be 1 and 5, or -1 and -5. So, because the coefficient here is just a 1. So the possible roots are plus or minus 1 and plus or minus 5. Take the factors of this over the factors of that leading coefficient. So those are the ones we would try. So let's just try 1 to begin with. So I'm going to take the coefficients, 1, 1, 3, -5. I'll start with 1 here. Now, another way to check quickly is just to plug in r equal 1 into the equation. If you plug in r equal 1, you get 1 plus 3 minus 5 is 0. If it comes out with the remainder of 0, that means it was a root as well. Okay, so let me show you what will happen if you pick one that doesn't work, because I'm getting really lucky here. Y'all may not be as lucky. Bring down the first term, multiply, add. multiply, add, multiply, and add. If this doesn't come out 0, that means we need to try a different one. -1 is not a root, which means r plus 1 is not a factor. So let me get rid of that attempt, and let's go back to our other one. Okay, we've already shown that 1 really does work because we plugged it in and got a remainder of 0. I'll show you with synthetic division. So bring down my 1, multiply, add, multiply, add, multiply, and add. Okay, so this gives us our factors. R minus 1, since 1 is a root, R minus 1 is the factor, and the remaining factor has those coefficients. It starts with an R squared. Plus 2R plus 5. Okay, so now, this one doesn't factor, the second factor doesn't factor, but we can use the quadratic formula to get the roots. R, it does factor, it doesn't factor with real number for the coefficients. It's going to be imaginary. Okay, R is going to be -2 plus or minus the square root of 4 minus 4 times 1 times 5, so minus 20, all over 2 times 1. So that's -2 plus or minus the square root of -16, so that's 4i over 2. So we have -1 plus or minus 2i. And then we also had r equal 1. So our roots are 1, -1 plus 2i, and -1 minus 2i. Okay, because of 1 being a root, I know that e to the 1x will be one of the solutions. So I'll have c1 times e to the x. Now because the complex number -1 plus 2i is a root, I'm going to have two solutions for that one and the one with the conjugate. So I'm going to have e to the -1x cosine of 2x, and then I'll have the other one as c3 times e to the minus x, so that's the alpha x. Alpha is -1 and beta is 2, and then sine of 2x. Okay, so that's going to be our general solution for the homogeneous equation with constant coefficients. Okay, so previously we looked at when we had distinct real or complex roots. Now let's look at when we have repeated roots. How do we get enough solutions for the nth order differential equations when some of the roots have a higher multiplicity than 1? So if R1 is a root that has multiplicity m, then we'll have e to the R1x will be one solution. But to get the other ones, to get m linearly independent solutions, we're going to multiply by x up to m to the x to the m minus 1 times. So you'll have x times the e to the r1x, x squared e to the r1x, up to x to the m minus 1 e to the r1x. And notice this gives us m roots that will be linearly independent. Okay, so what if it's complex roots? Remember, we know they automatically come in complex pairs. So if alpha plus beta I is a root, then alpha minus beta I is another one. But what if that one has multiplicity m? So we need to figure out how to get enough linearly independent roots to get enough for the order of the equation. So we know we'll start with e to the alpha x cosine of beta x and e to the alpha x sine of beta x. And now for each multiplicity, we'll multiply by another power of x. So you'll have x times e to the alpha x cosine of beta x and x times e to the alpha x sine of beta x, and keep multiplying by x squared, x cubed, all the way up to x to the m minus 1 to get enough roots so that this will be 2m roots to that auxiliary equation. Okay, so let's look at a couple examples. Okay, I see a linear fourth order, so I need 4 roots, homogeneous, constant coefficients. That's critical. That's why we know y equal e to the rx will be a solution. So I need to plug that in and get my auxiliary equation. So the auxiliary equation will be r to the fourth minus r to the third minus 3r squared plus 5r minus 2 equal to 0. Okay, we've got to factor that. Now the possible roots, because this is a fourth degree polynomial, we're going to factor this last term and take the factors of that leading coefficient, which are 1. So the only possible rational roots will be plus or minus 1 and plus or minus 2. So we're hoping that there are some rational roots to this. If not, then we're going to have a difficult time. So let's test them. Now I could test 1 quickly by just plugging 1 in for the r. So I'd have 1 minus r minus 3 plus 5 minus 2. And that one does work. So let's go ahead and use synthetic division, because by doing that I actually get the next factor. So I'm going to write down the coefficients. Okay, bring down my 1, multiply these values, add, multiply, add, multiply, add, multiply, and we get 0 remainder. Okay, so this row gives me the coefficients of the third degree polynomial that would be the other factor. So I know I have r minus 1, and then I've got an r cubed minus 3r plus 2. Okay, so let's see if we can factor this. Again, look at the last digit, the constant term, which is 2, and the first one is 1, so the only possible roots are plus or minus 1 and plus or minus 2 that are rational, so real numbers that are rational numbers. So those are the only ones we can try, so let's try 1 again. And you can easily see if you just added the coefficients, you would get 0, so 1 works again. So that's going to be good, because that's going to get us down to a quadratic. So we're trying 1 again. I bring down the 1, I multiply. Bring down the, add, multiply, add, multiply. And now I get that remainder of 0. So this is going to be the quadratic factor. So I have r minus 1 that was already previously, and then we have the other r minus 1 here. So that's r minus 1 is this factor as a result of that, and another r minus 1 here as a result of that. And so the other factor will be r squared plus r minus 2, which now we can just factor that. Let's see, that should be plus 2 minus 1. So we actually have 1 that has a multiplicity of 3. And then we have r equal negative 2 has just multiplicity 1. Okay, so our solution, our general solution to the homogeneous equation then would be, I'm going to go ahead and just do c1 e to the x, that's because r equal 1 is a root, plus c2 x e to the x, plus c3 x squared e to the x. It had multiplicity 3, so I need 3 terms from that. And then the last one will be c4 e to the minus 2x. And here's our general solution to the homogeneous equation. Okay, so now let's look at another fourth degree polynomial, fourth order differential equation with constant coefficients. So we're looking for those roots of the form y equal e to the rx. We have an auxiliary equation, which will be r to the fourth minus 8r cubed plus 26r squared minus 40r plus 25 equal to 0. The only possible rational roots would be plus or minus 1, plus or minus 5, and plus or minus 25. Now I'm going to tell you that if we try all those, it's not good. None of them are going to work. So I'm going to give you another little hint here. You're not going to have to just guess at complex roots. So if it ends up that you're going to have to go straight to complex roots, there's not real numbers to try, the rational roots to try, then they're going to probably give you one of them. So let's say that we are told that one root is 2 plus I. Just assume you're given that. Well, automatically we know that another root will be 2 minus I. And if I can get 2 of them, I can break this equation down to a quadratic. by removing that one factor. So let me show you how to do that. So I've got these two roots. If 2 plus I is a root, that means x minus 2 plus I is a factor, or r. Let me change that to r. Okay, and because 2 minus I is a root, I know that r minus 2 minus I is a factor. It's always r minus the root. Okay, so now if we multiply this out, I'm going to just use FOIL. It'll be r squared minus, I'll have 2 plus I from this product times r, and then this outer one, I'm going to have the minus 2 minus I, so that'll be my coefficient of the r term, and now I'm going to have the last two terms multiplied. That's going to be plus 2 plus I, 2 minus I. Okay, so this is r squared minus, notice the i's cancel there in the middle term, 4r, and now when you distribute these out, you're going to have 4 plus 2i minus 2i, and then minus I squared. Remember, I squared is equal to negative 1. So if I replace this with a negative 1, I'm going to have r squared minus 4r plus 5. That's the factor. Okay, we know that this then factors to r squared minus 4r plus 5. Now the trick is getting the other factor. Well, if we know that this polynomial divided by this will be the other factor, we can just use long division to find it. So I'm going to go ahead and do long division. I'm going to put the r squared minus 4r plus 5, which is the factor we know, and then I'll put this polynomial that we're trying to divide. Okay. I want to know what times this r squared gives me the r to the 4th, so that's easy, r to the squared. Now let's multiply back. Take the r squared times this entire term will be r to the 4th minus 4r cubed plus 5r squared. Subtract, the r4's cancel, minus 8r cubed minus negative 4r cubed will be a negative 4, remember we're subtracting, 4r cubed, and then 26 minus the 5 will be plus 21r squared, and I like to go ahead and just bring everything down. Okay, now I take this first term, r squared times what gives me this, which will be a minus 2r. Multiply back, take the minus 2r times this entire factor. So it's going to be minus, wait, where did I get the 2? 4. Minus 4r. I was looking at that second term, I guess. Okay, so that's going to be minus 4r cubed plus 16r squared minus 20r. Subtract. Okay, then minus 4r cubed minus negative 4r cubed is 0. We'll have 5r squared minus 20r. Remember, we're subtracting, so that's minus a negative 40r, minus 20r, and then plus the 25. And now what times r squared gives me the 5r squared? It's going to be 5. So multiply back, 5r squared minus 20r plus 25. And notice now we get a remainder of 0. Since we knew this was a factor, we knew the remainder better be 0. And so the other factor is whatever we got for the quotient here, r squared minus 4r plus 5. And it just so happened to be the same factor we already had, since we're trying to check what to do with repeated roots. Okay, so we already know what the roots are here, right? We were given those to begin with. So we know that the roots are r equal 2 plus I, 2 minus I, and they're repeated with this factor. Okay, so 2 plus I has multiplicity 2, as well as the 2 minus I. Okay, so that means that when we look at the solutions, the real solutions for these, we're going to have e to the 2, remember 2 is the alpha, and beta will be 1. So we're going to have e to the 2x cosine of 1x, and then we're going to have e to the 2x times sine of 1x. Okay, so those are two roots that we'll have. So I'll say c1 times one of them plus c2 times the other. I need another pair of roots to get the 4 for this fourth order equation. And I know that when I have repeated complex roots, I will multiply by the x. So c3x e to the 2x cosine of x plus c4x e to the 2x sine of x. And that's going to be our solution, the general solution to the homogeneous equation. Okay, so just try to get all the roots to the auxiliary equation, and when there's repeated roots, we know how to handle them now. Okay, now we're going to combine the differential operator notation with the solutions to the higher order linear differential equations that we were solving in a previous chapter. So we started with an equation of the form a y double prime plus b y prime plus c y equal to some function f of x. If we want to switch that to the differential operator notation, this would be a d squared y plus b dy plus cy equal f of x, or simply a d squared plus bd plus c of y equal to f of x. Okay, so this is the differential operator acting on y for this differential equation. And so we could call this some function L, so that this is L of y equal to f of x. Okay, so now what this method's going to do, it's going to be an alternative to the method of undetermined coefficients, or really it's better to kind of do along with the method of undetermined coefficients to help to determine what the form of the particular solution is. So what we're going to do is look at what's called an annihilator. An annihilator is a differential operator that, when performed on a function, creates 0. Okay? So it's a simple example. If I had the function f of x equal to 5, what operator would annihilate 5, would make it 0? Well, because the derivative of 5 is 0, that means that the operator would be just d. So d of 5 would be 0. So d is the annihilator of that constant term. And it would be true for any constant. So d is the annihilator of a constant. Well, what if we had a polynomial that was an x? Let's say an x plus 3. What differential operator would annihilate that? Would d performed on that function make it 0? Well, d performed on that gives you the derivative of x is 1 plus the derivative of 3 is 0. So it doesn't give you 0. But a d squared of that will make it 0. So d squared is the annihilator when we have an x to the first power in a polynomial. Now, what if we had an x to the second? Polynomial degree 2. Well, the annihilator would need to be d3 in order to take the derivative 3 times to make this function result in a 0. Okay, so polynomials will have annihilators that are d to the n plus 1 if n is the highest degree. So let's see where they have that. I don't see that they have that written here. So let's say dn annihilates polynomials of degree n minus 1. So anything of x to the n minus 1 plus dot, dot, dot. Okay, so now let's look at some of the other functions that we've been working with. When we were solving the differential equations before using the method of undetermined coefficients, we would always have expressions on the right that were either polynomials, exponentials, sines or cosines, or products of those. Okay, so we want to figure out what the differential operators are that annihilate each of those type of functions. So I know d to the n annihilates a polynomial of degree n minus 1. what about an e to the x? So e to the rx, or something of that form. What would annihilate that? Well, if this is our function, just taking the derivative of it won't annihilate it because it will still have the exponential function as a result. But the annihilator, the differential operator, d minus r, will annihilate that. And so I'm hypothesizing that this annihilates, just meaning that if I apply it to the function, it gets 0, e to the rx. So let me justify that. So to do that, let's take d minus r of e to the rx, which that's the derivative, remember just apply, derivative of e to the rx minus r times e to the rx. Well, the derivative of e to the rx is r times e to the rx minus the r e to the rx, and it indeed does give you 0. So our second one, so right now we have that d to the n annihilates polynomials degree n minus 1, and d minus r annihilates exponentials where it's e to the rx. Okay, so now let's look at sines and cosines. Well, while we're on this, let's go ahead and look at x to the powers to the e to the rx. Well, it ends up that if you have an x to a power times this, so something to the form x to the k e to the rx, then what annihilates that ends up being d minus r. You still use the same thing you needed for the e to the rx, but then raise it to a power. So if it's an x to the k, then we're going to need to go up to the k plus 1. So let's say that this was an x to the k minus 1 power, and so x to the k will annihilate it. Now, to show that, you would have to use specific values and actually square this thing out. You're, applying that power of that operator. So that's the adjustment when there's an x to a power times an e to the rx. So e to the rx, it's just d minus r, but if there's an x to the power times that e to the rx, you need to raise the power of the d minus r. Okay? Okay, so now let's look at sines and cosines. When we were finding roots, when we had the complex roots to those that auxiliary equation, we often had something of the form, we had alpha plus beta I as the roots. Okay, so what annihilates something when you have a, when you had this type of root, you ended up with an e to the alpha of t, or x, times cosine of beta x, and you had an e to the alpha x sine of beta x. So those were the solutions when your roots of the auxiliary equation look like this, the plus or minus. Okay, so what would annihilate that? Well, it ends up, the annihilator would be d squared minus 2 alpha d plus alpha squared plus beta squared. That would be the annihilator for these type of functions. Okay. Now the way they write it here, they use a little bit different notation. They use d minus alpha squared plus beta squared, which if you take d minus alpha squared, it's d squared minus 2 alpha d plus the alpha squared. So I've just kind of broken it up where here's the constant term, here's the d squared, and here's the d. Okay, so that's what annihilates things of this form. And so now what if there were powers of x also with this? Well, the same thing we did here when we had the powers of x with it, we just raised the power on the annihilator. Same thing here. Had there been an x to the k minus 1 with either one of these two terms, we're just going to raise this annihilator to the kth power. Okay, so we have, summarizing these, d to the n annihilates polynomials of the degree n minus 1. We have that d minus r annihilates e to the rx. We have that d minus r to the d minus r to the k annihilates x to the k minus 1 e to the rx. We know that d squared minus 2 alpha d plus alpha squared plus beta squared annihilates e to the alpha x cosine of beta x and e to the alpha x sine of beta x. And then if there were powers of x multiplied by either one of these, let's say there were powers of x to the k minus 1. Then this raised to the kth power would annihilate it. Okay? Okay, in one special case of this one, if your alpha were 0, which a lot of times we do have that case, so if you just have the cosine of beta x or the sine of beta x, meaning the alpha was equal to 0, then that means that the operator becomes d squared plus the beta squared. And that's what they have here. Okay, so now let's look at an example. Okay, so a linear operator said to annihilate a function if you apply the operator to f. So a is the operator, a applied to f gives you 0. Okay, and that's true for all x. So a will annihilate f, and what we're trying to find is we're trying to find the annihilator for the function f of x that'll be on the right side of a differential equation. So let's look at just a typical function f of x that might be on the right side. We want to find the annihilator. Well, take each term separately. Here's a 6x e to the minus x. So we know that e to the minus 4x is annihilated by d plus 4. But it has an x power in front of it. So we know that if it has an x power, a power 1 bigger, so d plus 4 squared will annihilate that 6x times e to the minus 4x. Now, if you wanted to prove that, you would show here that d plus 4 of e to the minus 4x will come out to be 0. That's what it means to annihilate it. This one, if you take d plus 4 squared, it will annihilate this function. That means you're going to be applying d squared plus 8d plus 16 to the function 6x e to the minus 4x. And when you do that, by doing the distribution, doing all those second derivatives of that, and 8 times the first derivative, you will get 0. Okay, so that means d plus 4 squared annihilates this term. Well, what about this term over here? It's an exponential times the sine of 2x. Well, we just saw that the operator that annihilates this is of the form d squared minus 2 alpha d plus alpha squared plus beta squared. Well, in this particular problem, the e to the x, that means that the alpha was equal to 1. The beta is equal to 2. It's the number times the angle and the sine of the cosine function. Remember, the e to the alpha x sine of beta x, or cosine of beta x. So the alpha is 1, the beta is 2. So that means the operator that it would annihilate this term will be d squared minus 2d plus 5. Okay, so now, once we have annihilators for each of these two terms, we can find an operator which will be the product of the two, d plus 4 squared times d squared minus 2d plus 5 will annihilate that sum. Okay, so find the annihilator for each term, and then the product will annihilate the entire sum. Now, had there been a constant term over here plus a 7, I would have needed a d. Okay, had there been just a 7x squared term, I would have needed d cubed to put alongside here. Okay, so that's if this 7x squared had been added to that. Okay, so be able to get an annihilator for a function f of x. Okay, next we'll look at how to actually solve the equations using these annihilators. Okay, so let's first solve this equation using the method of undetermined coefficients that we did previously. Okay, the first step here was to solve the homogeneous equation. Which had been y double prime minus y equal to 0. Okay, our auxiliary equation was m squared minus 1. So we got m equal 1 and negative 1. So that the solution of the homogeneous equation was y equal c1 e to the x plus c2 e to the minus x. And we call that a complementary solution. Okay, so that's the solution to the homogeneous equation. Okay, then we found what the form of the particular solution looked like based on the function f of x. Well, an x times e to the x meant that we needed to have a term of the form ax plus b times the e to the x. Okay, so that's the type of term that's needed because of this part, this expression. And then when there's a sine of x, we had to have a sine of x plus a cosine of x. Constant. So c times sine of x plus d times cosine of x. Okay, so that was the form. And you could do these separately if you wanted to. You know, and that's usually the way we did it, using that superposition property. Do this one and then do this one and just use each of these separately. So let's do that and solve for the a, b, c, and d. So I'm going to first solve y double prime minus y equal x e to the x using the form yp equal ax plus b e to the x. Okay, so I need to have the second derivative to plug in here. So y prime, I'm going to need a product rule. So it's going to be the derivative of ax plus b, which is a e to the x, plus the ax plus b times the derivative of e to the x. So using the product rule. And now y double prime, now let me simplify that a little bit. Notice that that's the same thing as ax times e to the x. And I have an a e to the x and a b e to the x that just are constant. So plus a plus b e to the x. So just simplifying it a little bit. Now the second derivative. The first one requires the product rule. So a times e to the x plus ax e to the x. And then this one does not require the product rule. It's just going to be a plus b e to the x. So if I want to simplify that, combining like terms a little bit, I would have the ax e to the x. And then I have a 2a plus b e to the x. Okay, so now let's plug those in. Y double prime would be ax e to the x plus 2a plus b e to the x minus the y, which will be ax plus b e to the x, and that should equal to x e to the x. So, like terms on the left, I have an ax e to the x, and I'm going to have a minus ax e to the x here. Those cancel. Then I have a 2a plus b e to the x, and then I have a minus b e to the x. So the b terms would cancel. So I end up with just 2a e to the x on the left side equal to x e to the x. Oops, that didn't work. So something happened where I'm not going to be able to get that. That's when you have to look back and think, oh, did this overlap the solutions to the homogeneous equation? Okay, and it did, because we had an e to the x term here, and over here we had a b e to the x term. So this overlapped this part here, right? This was ax e to the x plus b e to the x. So what we had to do to adjust for that was we had to multiply by an extra power of x. Okay, so this became an ax squared plus bx e to the x. So that becomes the form because of the overlap with the homogeneous solution. Okay, so let's go back. That just reminded you why we had to make that adjustment, because there's no way we would ever get this to be true. Okay, so now let's find y prime and y double prime again for this adjusted solution. Okay, so y prime, I'm looking at this form here. The first derivative is 2ax plus b times e to the x. We're using the product rule, first times second. So this is the derivative of this, is the first part, and then e to the x, plus, and then ax squared plus bx times the derivative of e to the x. And cleaning that up a little bit, we have an ax squared term. I have a bx and a 2ax, so I have a plus 2a plus b x e to the x. Yeah, I might as well just separate these out. No, I can do it this way. And then we have a b e to the x. So this is the coefficient of the e to the x if I combined it that way. Check it again. Here's the ax squared. We have a 2a and a plus b for the x, and then we have just the b. Okay, so that's the y prime. And now the y double prime. The derivative of the first term will be 2ax plus 2a plus b times the e to the x plus the first term times the derivative of e to the x. Okay, so now combining that, we have one x squared term, so ax squared. The x terms, we have a 2a plus bx, and we have a 2ax here, so that's going to be a 4a plus bx. And then our constant terms, we'll have a 2a plus a b there and another b over here, so we have a 2a plus 2b. And then all that times e to the x. Okay, now we're ready to solve. We're solving just this part. We're just looking at this part of the solution. Oops, I didn't put my extra x in here. Okay, so we have y double prime minus y equal x e to the x. I'm going to find the solutions. So y double prime will be ax squared plus 4a plus bx all of that times e to the x minus the y, which is ax squared plus bx e to the x, and we should just get x e to the x. Okay, look at the x squared terms. I have an ax squared minus an ax squared. Those cancel. Now all these are times e to the x. So if I want to just get rid of my e to the x's, I can, because e to the x is times everything on both sides. So I have the ax squareds cancel. The x coefficients are here, here, and here. So I'm going to have 4a plus b minus the b. So this b and this b cancel. So I just end up with 4ax equal 1x. So that means the a is going to be 1/4. And now the last ones, I have 2a plus 2b. Here's the constant term. There are no constant terms here, so that has to be 0. So that means I have 2 times 1/4 will be 1/2. This is an a. Plus 2b is 0. So that means that the b is going to be negative 1/2 times 1/2 is negative 1/4. Okay, so that means that my solution for y sub p was equal to 1/4 x squared minus 1/4 x e to the x. Or we could write it as x times negative 1/4 x minus 1/4 e to the x. If I want to emphasize that x times the ax plus b times e to the x. Okay, the next part we need to solve is this solution. So we want to solve y double prime minus y equals sine of x, and we know that the form of the particular solution, there was no overlap with the complementary solution, so it'll just be c sine of x plus d cosine of x. The y prime is c cosine of x minus d sine of x, and the y double prime will be minus c sine of x minus d cosine of x. Okay, so plugging in, we get minus c sine of x minus d cosine of x for the y double prime, then minus the y, which is this part, c sine of x minus d cosine of x, and that has to equal to sine of x. Okay, so the sine terms, we have a minus c and a minus c, so minus 2c sine of x has to equal the coefficient here, which is just 1. So c is negative 1/2. Minus d cosine, so minus 2d will be the coefficient of the cosine, and there are no cosines over here, so it has to be 0. So d is 0. So our particular solution, yp, then, will be minus 1/2 sine of x. Okay, so now, putting it together, getting the solution for this entire equation, we're going to add this solution and this solution together. So we'll have y sub p equal x minus 1/4 x minus 1/4 e to the x minus 1/2 sine of x. And then if we want the full solution, we would also add the complementary solution to it. So we would have that the general solution is y equal c1 e to the x plus c2 e to the minus x plus x times minus 1/4 x minus 1/4 e to the x minus 1/2 sine of x. Before I go any further, let me go back here and realize I did not have a negative here, and when I wrote this it looked like a negative, so I just made a mistake on writing it. That should have just been a positive 1/4. And so this should have been a positive 1/4. There was no negative there. So just 1/4 x minus 1/4 times the x times the e to the x minus that 1/2. Okay, so now how will this annihilator method help us with this problem? The annihilator method helps you to determine what the form of the y sub p will be. Okay, you want to figure out what is the annihilator for the function over here, and we're going to get that annihilator and form a new homogeneous equation and look at its, because if we just have a homogeneous equation, it was real simple to get all what the solution is going to be for that. It was when we had to look at the particular and adjust it because of the homogeneous equation that we usually had a problem, and notice we missed the x because we didn't go back and check to see if there was an overlap with the homogeneous equation. So the method of undetermined coefficients works fine. This method just might help you to catch those adjustments that you need to make. So let me go over what this method will look like. Okay, so we already know what the solution comes out to be, and we know how to get it. Really, what it's going to help us with is just getting the form of the particular solution. Okay, so we noticed for this particular equation that this was, which I just erased it, that was the form of the solution of the homogeneous equation, which is reflected down here in these first two terms. Okay, and then this was our particular solution, the y sub p. Okay, so what the annihilator method says is look at your equation, the function on the right, and determine the annihilator for that. Well, the annihilator of the x e to the x, remember e to the x has annihilator d minus 1. So this annihilator e to the x. And when you multiply by an extra x, that means you have to raise the power to be one more than what, if that's a degree 1 term, I need this to be a power of 2. Okay, so d minus 1 squared will annihilate x e to the x. Okay, now I've got a sine of x term. I know that the beta then here would be 1, and the alpha is 0, because we're always expecting an e to the alpha x sine or cosine of beta x. That's what the form is of those, the solution. And the alpha, if it's just a sine of x, that means the alpha had to have been 0, and the beta here would be 1. So the annihilator is of the form d squared minus 2 alpha d plus the alpha squared plus beta squared. That's the form of the annihilator for something of this form. So using alpha equals 0 and beta equal 1, that becomes d squared plus 1. Okay, so now the annihilator that would take care of this whole right side then will be d minus 1 squared times d squared plus 1. That annihilates x e to the x plus sine of x. Okay, so now let's start. I'm going to rewrite this equation using the differential operator notation. On the left side, I would have d squared minus 1 of y, right? Because this is d squared of y minus 1y. Okay. I could factor that. That's d plus 1, d minus 1. Now let's apply the annihilator for the right side, which will be d minus 1 squared, d squared plus 1 to both sides. On the left side, I'm going to have d plus 1, d minus 1. Well, I've already got a d minus 1 here, and I'm going to apply that, so I'm going to have a d minus 1 cubed. And then this applied to the right side. And what did it mean to be an annihilator? That means that if you apply this operator to the function, if it's the annihilator for this function, that means that right side is 0. Okay, so now we've got a homogeneous equation. What is the solution, the complementary solution to this homogeneous equation, or the general solution of the homogeneous equation? We would have y equal c1 e to the minus x for this factor. This factor appears 3 times, so we know that we would have a c2 e to the x, but because it appears 2 more times, we would have a c3 x e to the x and a c4 x squared e to the x. This results in a, because that's the roots to d squared plus 1 are 0 plus or minus I, which would give us the solution e to the 0x sine of 1x plus e to the 0x cosine of x. So let's see if we added C5 and C6 for those coefficients. That would be the solution, the general solution for this homogeneous equation. Note the answer that we got over here that I just erased part of. We have the C1 e to the x plus the C2 e to the minus x, and then plus this was the particular solution. Okay, so the C1, actually this is part of the equal sign. The C1 e to the x here is right here. The C2 e to the minus x is covered here. This is an x squared e to the x here's the x squared e to the x, which is this. This x with that minus 1/4 e to the x is covered here. And then our sine of x and cosine of x, which were both possible in that form, it's just the last one came out to be 0, or here. So looking at this particular solution, really the advantages, the particular solution up here was ax squared plus bx e to the x plus c sine of x plus d cosine of x. And that's exactly what we have here, except I didn't put this, I put 1, that's 41. It's the exact same form for the y sub p. If you use the annihilator and then look at the homogeneous equation that you have on the left side and come up with that complementary solution, because it's done in conjunction with what the solution was to the previous homogeneous equation, which had that d plus 1, d minus 1 already in it, it automatically makes the adjustment for the y sub p. So if you want to use the annihilator to determine what the form is for the particular solution, you still have to plug it into the original problem to figure out what those coefficients, the C3, C4, C5, C6 are. But it's one way to get this particular solution if you struggle with making the adjustments based on what the homogeneous solution was. Okay, so now let's look at it one more and just do it with the annihilator method. Okay, so using the annihilator method, I'm going to just rewrite this whole thing in the differential operator form. So this is going to be d cubed y minus 3d squared y plus 4y. Okay, and factoring this comes d cubed minus 3d squared plus 4y. Oh gosh, we'd have to factor that thing out to get that as a factored form for that. Okay, we would have to do that if we were just solving the homogeneous equation, the original problem anyway. So let's just guess. The only possible rational roots of this equation are going to be 1, 2, and 4. 1, 2, and 4. And I can see 1's not going to work because if I plugged in 1, it's not going to have the coefficients equal 0. And 4 may or may not. Let's just try 2. So I'm going to go back to the, you're doing long division. D minus 2 is the factor. I'm trying to see if that's the factor of this polynomial. I'll put 0d plus 4. When you were in algebra, you did something called the synthetic division, where you would just put the 2 here, and you just put the coefficients of these, and brought the first thing down, multiply, add, multiply these two, -2, add, multiply, -4. If you get a 0 there, that means it really was a factor. So d minus 2 is a factor, and here's the other factor. So that means this thing factors to be d minus 2 times d squared minus d minus 2. I just take the coefficients here of this second factor. I'm just going to get this so we'll be in better shape before we... Okay, and this is d minus 2 times d plus 1. So -1 would have worked for that too, it looks like. Okay, so this is d minus 2 squared, d plus 1, y equal x e to the x. There's my 2 here. Okay, so instead of looking at the homogeneous solution and then having to adjust because of this x e to the 2x, I'm going to just look at the right side and figure out what is the annihilator for this. So I'm not having to worry about the homogeneous solution, first. The annihilator for this, because of the e to the 2x, is d minus 2. And because of the x multiplied, it's going to have a power of 2. So d minus 2 is the annihilator of the right side. Apply that to both sides. I know this right side, when I apply that annihilator to the right side, it's going to give me 0. And so now I have d minus 2 to the 4th, d plus 1 times y equal to 0. So what would the form of this solution be? Well, we have the d plus 1, so we know it's going to have y equals c1 e to the minus x. And now 2 appears 4 times, so plus c2 e to the 2x plus c3x e to the 2x plus c4x squared e to the 2x plus c5x cubed e to the 2x. Okay, so that's going to be our form. We know that the homogeneous solution to the original problem would have had these terms in it. That's where your coefficients are going to actually come from. So we have a 2 of the 2, so that means this right here. This was the solution to the original homogeneous. So that means these are what will be the y sub p. So the y sub p will be a constant, and I wouldn't use C4, C5 because of the subscripts. I would use just an a and a b. A x squared e to the 2x plus b x cubed e to the 2x, and plug into the original differential equation, which is up here. Okay, so let's do that real quick. Not real quick. I'll let you do that. Or you can stop now. I'll go ahead and work through it. But you've got to find up to y triple prime, and you're going to be using the product. I'm not going to go through that. I just want you to see how it would be the same thing as if you were doing this with the method of undetermined coefficients. I just want you to see how you can get what that format is of the y sub p without doing it for the original one and then adjusting it because of the overlap. We would have had an overlap. With this x e to the 2x, we would have said that was an ax plus b e to the 2x. And because this e to the 2x appeared here and the x e to the 2x, we would have had to multiply it by an additional x squared, and that's exactly what we have here. The x plus b times an extra x squared. So if you like the method of undetermined coefficients and are comfortable with getting the form of that y sub p when you take into account the homogeneous solution to the original problem, then you don't need to use this. This is just an alternative way to get the form of the y sub p, and then you just plug it in and keep going. We got to solve for the a and the b, and that will take a lot of applications of the product rule. Okay, so the last thing here is just kind of summarizing. You don't have to use it directly. The annihilator method just tells you how to upgrade your method with the constant coefficients. So it's telling you what to do with that y sub p, and that's just a form that gives you some forms in it. So that's the annihilator method for solving just a single equation. Okay, the method of undetermined coefficients and the annihilator method only work for linear equations that have constant coefficients. Okay, and when that non-homogeneous term on the right side is a solution to some homogeneous linear equation. Remember, it had to be polynomials, exponentials, or sines and cosines. So what we want to do now is we want to use another method, the method of variation of parameters, to generalize the higher order linear equations that have variable coefficients. So you need to use variation of parameters anytime the equation has variable coefficients. Okay, so we're looking to find a solution of the standard form equation that looks like this. Remember, this Ly of x is just a way to write that linear nth order differential equation. And those coefficients, once you have it in standard form, have to be continuous as well as the g. Okay, so a general solution we've already found will be of this form: c1 y1 plus c2 y2 all the way up to cn yn. So we found our n roots, and we've come up with that general solution of that nth order homogeneous equation. Okay, so now the method of variation of parameters tells us that there will be a particular solution. We've got the solution to the homogeneous equation. We now have to find a particular solution, and the form of it will look like this. It's going to take these solutions that were of the homogeneous equation and multiply those not by constants but by functions. So we're going to have some v1 function of x times the y1 all the way up to some vn of x times the yn. So our job then will be to find these v's that have to be multiplied by those functions that we got for the homogeneous solution. Okay, so now those v's must satisfy this system. And so what we want to do then is we want to take this system and solve it using Cramer's rule. Now, if you recall, Cramer's rule says that our solutions here are for the v sub I primes. Okay, so what we do is we take the coefficient of all these v's. So we have v1 prime all the way to v sub n prime in each equation. Okay, so form a determinant that has all those coefficients. So we're going to have y1, y1 prime. The first column will have all these y1s to, start with y1 in the first row and then have their derivatives below that. The last column will have yn, and then it'll have all of its derivatives below that. So the coefficients of these, the v prime of n, will be the derivatives of the yn. Okay, so now if you recall, all this is the Wronskian. It's the Wronskian where we put those solutions, the y1 to yn in the first row, all the first derivatives in row 2, all the second derivatives in row 3, and so on, until we get this n by n matrix. So Cramer's rule just says that we need to find the solution to this system, and the way you do that, the way you set up Cramer's rule, is the first variable, v1 prime, will be another determinant where you take if we're doing v1 prime, the very first column, we're going to replace column 1 here with this set of solutions. So we'll have 0, 0, all the way down to g. All the other columns will stay the same as what they were for this Wronskian. So we'll have y2, y3, all the way over to yn. And we'll continue with the derivative so that this will be y2, the nth derivative of y2, and this will be the nth derivative of yn. Okay, so this will be the same as the columns 2 through n of the Wronskian. All we've done is replace the first column with these solutions from 0 to g. Now remember, the g has to be the result of getting it in standard form, so you have to divide by that first leading coefficient to get the proper g. Okay, so that's going to be how we get v1 prime. We take that determinant over the Wronskian. So we'll have to calculate this, the Wronskian, the determinant for it as well. The v2 prime, well again, the bottom will be the Wronskian. The top will be the determinant. We'll keep y1 in column 1. So we'll have y1 prime here all the way down to the nth derivative of y1. Then in column 2, we're going to have that 0 down to the g. And then in column 3, we'll have y3 down to the nth derivative of y3. And we'll do that all the way over to the yn, and then the nth derivative of yn in that last row, last column. Okay? And that's how you get V2 prime. And you just continue. You're just replacing the nth column to get the V sub n prime. Now, they give you a formula here where you just have to put the G here. That'll work out as well. They're just taking into account the fact that you have zeros in all the other entries of that column. So I'm going to do it by setting up Cramer's rule. You can use that formula as well. So what we're going to do is we're going to get the V primes, and then we've got to get the V's though, because we know the general solution is going to be the V1 Y1 plus V2. This is the particular solution. V2 Y2 to Vn Yn. So once we get the functions V from integrating these results, we're going to then multiply them by the y's that we used for the row 1 of the Wronskian. Okay, so let me show you how that's going to work. Let's demonstrate it with an example. Okay, I want to find a general solution to the Cauchy-Euler equation. Okay, notice here, this is a third order linear differential equation, variable coefficients. Okay, that means the solution is not e to the rx. When it has special coefficients that are variables, where the power of x matches the order of the derivative. See, this is a third order derivative times an x cubed. Second order derivative times an x squared. When those all match like that, that's the Cauchy-Euler form. Cauchy-Euler form says that the roots are of the form y equal x to the r, not e to the rx, but x to the r. So I'm going to remind you how to get the roots for the Cauchy-Euler. We want to find the general solution to the homogeneous equation first. So we've got x cubed y triple prime plus x squared y double prime minus 2xy prime plus 2y equal to 0. We want to solve this first. Okay, and I'm going to do that by plugging in this solution. So we have y equal x to the r. That means y prime will be r x to the r minus 1. Y double prime will be r times r minus 1, x to the r minus 2. And y triple prime will be r minus 1, r minus 2 times x to the r minus 3. So plugging those in over here, we have x cubed times r minus 1, r minus 2, x to the r minus 3, plus x squared times y double prime, r times r minus 1 times x to the r minus 2, plus minus 2x times y prime, which will be r x to the r minus 1, plus 2 times the y, which is x to the r, equal to 0. Now, multiply the x powers together in each term, and you're going to notice each one of them will have an x to the r. So you're going to have an x to the r, and I'm going to go ahead and multiply out r times r minus 1 times r minus 2. That's going to be r cubed. It'll be minus 3r squared plus 2r. Okay, so plus 2 and then times the r. And then plus, now I have an x to the r here, which would be times r squared minus r. Then I'll have minus 2 times x to the r times just a single r, plus 2x to the r equal to 0. Now factor out the x to the r out of all the terms. You're going to have r cubed minus 3r squared plus 2r plus r squared minus r minus 2r, 2r, and then plus a 2. Okay, we're assuming that x is not 0. Okay, and so the only way this will be 0 is if this expression is 0, which is just r cubed. Let's see, here's our r squared term, so we have minus 2r squareds. These cancel, and we have minus r, and then we have plus 2. Okay, so we need to find the roots. Oh, that's an easy one. That's factoring by grouping. Take the first two terms, take out an r squared, so that's r squared times r minus 2. And now I'm going to take a minus 1 out of the last two terms. Now I can take the r minus 2 that's in common out of both, and I have r squared minus 1, which now factors. Okay, so we get the roots 2, -1, and 1, which tells me x to the second, x to the -1, and x to the 1 are the roots. So our general solution to the homogeneous equation will be y equals c1x squared plus c2x to the -1 plus c3x. Okay, so now we've got our y1, y2, and y3. Now the order you put these in doesn't matter as long as you're consistent. When you get the v's, you've got to multiply them by the proper y. Okay, so the particular solution is going to be of the form v1 times y1, which will be the x squared, plus v2 times the y2, which is x to the -1, plus the v3 times the y3, which is times x, and that's what we're looking for. So we need to find the v's, and we know that the v's, okay, let's start with the Wronskian. The Wronskian will be the determinant that you get by putting the y's in the first row, so x squared, x to the -1, and x, and then taking the derivative. Since there's 3, we need 3 rows. So we'll have 2x minus x to the -2 and 1. Now the second derivatives, since there's our Wronskian. Now here's the important part. Before we can get our g, we have to divide by this leading coefficient. So to find our g of x will be the x cubed sine of x. Remember, it had to be in standard form over the x cubed. So our g is going to be just sine of x. Okay, so I'm going to set up the different determinants to find the v1, the v2, and the v3. To find v1, I'm going to use the determinant, I'll call it w1, which is going to be replacing column 1 with 0, 0, sine of x. Now the book's using 0, 0, 1, and then they multiply by sine of x later. I'm just going to go ahead and keep it this way. Then x to the -1 minus x to the -2, 2x to the -3, and then x, 1, and 0. Okay, then we'll have to evaluate that determinant. Our W2 will be taking the Wronskian, but replacing column 2. So keep column 1 in the Wronskian. Column 2 becomes 0, 0, sine of x, and column 3 will be x, 1, 0. Okay, and then our W3. So that's how we're going to get the V3. Column 1 is the same as the Wronskian. Column 2 is the same as the Wronskian. Column 3 is the same as column 3 will be the 0, 0, sine of x. Okay, now let's evaluate each of these determinants. I'm going to pick the column that has the most zeros, just because it's the simplest to evaluate that determinant. So for this one, using column 3, I need to make sure I get my signs right. This is position 1, row 1, column 3. So this is going to be a positive term. This one corresponding to this entry will be negative, and this one will be positive. Those are for evaluating the determinant. So we're going to have x times the determinant. Now mark out the row and column containing the x, and you're going to have 2x minus x to the -2, 2, and 2x to the -3. And then I have a minus the 1. I'm expanding on column 3. And then I'm going to take the determinant that I get by marking out row 2 and column 3, the one that contains -1. And so I'm going to have an x squared, x to the -1, and then 2 and 2x to the -3. Okay, so we're going to have x times 4x to the -2 plus 2x to the -2, and then minus the 1 times 2x to the -1 minus 2x to the negative 1. Okay, so those cancel out. So I end up with 6x to the negative 2 times x, which will just be 6x to the negative 1. So that's the Wronskian. So when we find the V1, the V2, and the V3 primes, they'll all be divided by that. Okay, so now I want W1. I'm going to use column 1 to expand it. Now, let's get the signs. This is row 1, column 1, so it's going to be positive. Row 2, column 1 will be negative because the indices add up to an odd number, and then this one will be row 3, column 1, which are also even. So always alternate, just get the first one correct. Okay, so now this will be 0 times a determinant plus 0 times a determinant plus sine times the determinant we get by marking out the row in the column containing that sign. So we're going to have x to the negative 1, x, negative x to the negative 2, and 1. X to the minus 1 minus x, that would be plus, because it's minus the negative x to the minus 1. So this will be 2x to the negative 1 sine of x. W2. I'm going to expand on column 2 here. Now this one is row 1, column 2. So this one's going to start negative. This one will be positive, row 2, column 2. And this one will be negative as well. So the only one that matters is the last one, of course, since the others are 0. So we're going to have minus sine of x, and then times the determinant we get by marking out the row and column containing that entry, which is that. So this is going to be x squared times sine of x, since we had a negative in front as well. Okay, and now W3. I'm going to expand this one on column 3. I need to get my signs right. This is row 3, column, or row 1, column 3, which will make this one plus, this one minus, and this one plus. So expanding on column 3, we get sine of x times the determinant we get by marking out the row and column containing that sign, which will be this. So we have sine of x times negative 1, x squared times x to the minus 2 is x to the 0, and then we'll have minus 2. So that'll be a negative 3 sine of x. Okay, now let's form our V1 prime, V2 prime, and so on. I know the V1 prime will be the W1 over the W. W1 came out to be 2x to the negative 1 sine of x. And W came out to be 6x to the negative 1. So that's going to be just 1/3 sine of x. So V1 will be easy to find. V2, let's just go ahead and do one at a time here. V2 prime will be W2 over W. So that'll be x squared sine of x over the W, which will be 6x to the negative 1. So this is going to be 1/6 x cubed sine of x. That's going to take a little bit of integration by parts. And then let's do V3 prime. Will be W3 over W, which will be minus 3 sine of x over W, which is 6x to the negative 1. So this is going to be negative 1/2 x sine of x. So that'll take one round of integration by parts. Good review. Okay, so now, the first one, V1 will be easy. We just need to integrate. We're going to have 1/3 negative 1/3 cosine of x. Now don't worry about a plus c. All we need is a solution. We don't need all possible solutions. So negative 1/3 cosine of x. Okay? So that's what we'll put right here times the x squared once we get the other ones. Okay, V2. We need to integrate here. Now, we're going to take several rounds of integration by parts. So I'm going to use my space over here. Okay, let me remind you of integration by parts and find V3 first. And then I'll show you how to do multiple iterations at once. Okay, so we have V3 here, and we have V3 will equal to negative 1/2 times the integral of x sine of x. We're going to say that u is just the x, and the dv is sine of x. Okay. Integrate the dv to find v. So v then will just be negative cosine of x. And now find du, which will be simply 1. Okay, so this integral here then becomes the uv, which will be negative x cosine of x, minus v du, so it'll be minus the integral of minus cosine of x times 1. Okay, so we've got negative 1/2, negative x cosine of x. I can pull this minus sign out, make those positive. The integral of cosine is just sine, so this will be plus sine of x. So our V3 comes out to be positive 1/2 x cosine of x minus 1/2 sine of x. So that's one iteration of integration by parts. Okay, now the other one, with that x cubed, you know it's going to be several iterations. So I'm going to show you how to do them all at once. We're going to form a little table. We're going to have our u. Some people call this the tabular method. I'm going to put the x cubed. Okay, and I know that the dv is going to be sine of x. Okay, let me simplify just a little bit. This will be v2 equal to 1/6 the integral of x cubed sine of x. So that's where we're starting. Okay, so form our table by taking derivatives of the u until you get to 0. So we're going to have 3x squared, then we're going to have 6x, then we're going to have 6, and then we'll have 0. At the same time, integrate the dv's until you get enough rows. So the integral of sine will be minus cosine. The integral of minus cosine will be negative sine. The integral of negative sine will be cosine. And then one more time will be just sine. Okay, we just happen to be back where we... Okay, so now the answer will be the product of the diagonal. So remember, this will be our v down here. So we're going to do, here's our u times our v, that product, and it's going to be positive. Then we're going to go ahead and do the next round. Would have made this the u and this the v, but this time it's going to be negative. And then this group would be positive, and then this final one would be negative because the next one would have had a 0 times something, which we don't need. Okay, so this integral, v2, will be the 1/6 times, we're doing the u times v each time, so it's going to be minus x cubed cosine of x, just taking this first product, and then minus this product, so it's going to be another minus, so that'll make it a plus 3x squared sine of x, and now we'll be plus this product, and then it's going to be minus this product. And we just did 3 or 4 iterations at once. Okay, so that's my V2. So we'll have, let's see if there's no terms to combine in there. So it's going to be minus 1/6 x cubed cosine of x plus 1/2 x squared sine of x plus x cosine of x minus sine of x. And that's what we're going to use for our V2. Okay, now we're ready to form the final solution. We know that it's going to be yp We're getting the particular solution here. Make sure we get the order right up here. We had x squared, x to the minus 1, and x. So v1 x squared plus v2 x to the negative 1 plus v3 times x. Okay, so just take your v's. v2 times x to the minus 1 plus the v3 times x. Okay, simplify that. Okay, now everything in this second parentheses will be multiplied by the x to the minus 1. So that's going to be a minus 1/6 x squared cosine of x plus 1/2 x sine of x plus cosine of x minus x to the negative 1 sine of x. And then the last one, 1/2 x squared cosine of x minus 1/2 x sine of x. Now let's see if we have some terms that we can combine. Okay, we have x squared cosine of x here, here, and here. We have a negative 1/3 plus a negative 1/6, which is negative 1/2, plus another positive 1/2. Those three terms cancel out. Let's see, we have a 1/2 x sine of x and a minus 1/2 sine of x. Those two terms cancel out. So our yp is simply cosine of x minus x to the negative 1 sine of x. Now, go back and get your general solution to the homogeneous equation, and then we'll have our general solution to the non-homogeneous equation will be y equal to y sub p plus the homogeneous solution. And there we go. And now we're going to look at Laplace transforms. You studied two transforms back in Calculus 1. One transform was differentiation. Differentiation took a function, such as x cubed, and mapped it to another function, 3x squared. Okay, another one, integration, was a transform. It took a function and it mapped it to another function. So a transform will take a function and map it to another function through some rule that's defined. The Laplace transform is an integral transformation. If f of t is a function, and it's defined on some interval from 0 to infinity, the Laplace transform of that function f will be the function that results from taking the integral of e to the minus st times the f of t that you started with. Okay, so the resulting function here will be the function that's transformed under this integration. We call that capital F just so it relates more directly with the name of the function that we started with. But notice that if we're integrating a function, we have an e to the minus st f of t, where t is and s are both independent variables. If we're integrating with respect to t, we're going to get a function of s. Okay, so the Laplace transform takes a function, this f of t, and maps it to a function, capital F of s. And the rule to define that will be this integration. Now the domain of f of s will be all values for s so that the integral is going to exist. So I'll point that out as we find the Laplace transform for some of these basic functions. And we'll use the notation, the Laplace transform for f will be denoted either as a capital F or this symbol Laplace transform of the function f. So that will be the capital F, and it'll be a function of s. Okay, so let's see how that's applied. Let's find the Laplace transform for just the constant function 1. So I'm going to take this integral, so capital F of s will be the integral from 0 to infinity of e to the minus st. You'll always use that. That's called the kernel, whatever's with that function in your definition of the integral. And then we'll put the function 1 for the f of t here. And we're integrating with respect to t. Now, since that's just integrating, multiplying by 1, this will be just the integral of e to the minus st. Okay, so let me remind you of a basic integral from Calculus 1. If you want to integrate e to a number times t, it's 1 over the a, whatever numbers times the t, e to the at. Now that's just a simple u substitution, letting the u be the at. Okay, so for this particular problem, we're integrating with respect to t, so that's our independent variable. Minus s is just a constant in this case, so that's just the multivariable calculus. So if you haven't had Cal 3, that might be kind of new. You just treat the s as a constant. So the integral of this will be minus 1 over s e to the minus st. And now we want to evaluate from 0 to infinity. Now, recall when you had an infinity as one of the limits of integration, that's an improper integral. So technically what this really is, it's the limit where we use the value b in place of the integral, and then we let the b approach infinity. So now when we evaluate, we'll plug in b for the t, so we'll have minus 1 over s e to the minus s times b, and now plug in the 0 for the t, so minus a negative 1 over s e to the 0 and this will be just plus 1 over s, since e to the 0 is 1. Now to integrate this, or to see if it exists, recall the exponential function. If you remember, the graph of the exponential function looks like this if the exponent's positive, so that's y equal to e to the x, or it's going to look like this if the exponent's negative. So if we're trying to see if it exists or not, as b goes to infinity, where the b is in the exponent, this expression will be 0 only in this case where the exponent's negative as b goes to infinity. Otherwise, it's going to go to infinity as b gets, as we let the value of the exponent get bigger and bigger. So to see if this converges, this will only converge or exist, be a real number, if the exponent remains negative. Okay, so let me rewrite this in another form. That's minus 1 over s times 1 over e to the sb. Okay, so now you see as b gets larger and larger, this denominator is getting larger and larger, going toward infinity. So then this term would actually approach 0. So 1 over e to the sb approaches 0 as b goes to infinity. That's assuming that the s is positive. If the s is not positive, that means that it should be, that expression should be up in the numerator. So for this to exist, for it to approach 0 as opposed to infinity, the s is going to have to be greater than or equal to 0. But because we've got s's in the denominator, the s has to be greater than 0. So this is only going to exist, and the integral will only exist if s is greater than 0. So that's going to be our restriction on this function. The s must be positive for this to exist. So this limit approaches 0, and then we result with just a 1 over s. So that means that the Laplace transform of the constant function 1 is just 1 over s. And so that's going to be our first one. Okay, now let's look at another, just a polynomial term t. Okay, the Laplace transform for t will be the integral of e to the minus st times the function t, that's my f of t, dt, from 0 to infinity. Now again, this is a limit as b goes to infinity of the integral from 0 to b of e to the minus st times t. Just changing it because of the improper integral that we have because of the infinity in the limit, upper limit. Okay, now this is going to get to be old, writing that limit every time. So just as a matter of convention, as long as you understand that that infinity in the upper limit, you can't plug infinity in, it's not a number. But what you're always doing is you're always looking at that value getting larger and larger. So we'll tend to just drop, I'll go ahead and write it down this time, but we're going to drop using that notation and keep just the infinity as the upper limit, and then even as we're evaluating it. Just keep in mind you're really finding a limit as the value is getting larger and larger. Okay, so now how do we integrate? We want to find the integral of this. Remember that the s is a constant. So we have something like e to the 2t times t. Because we have a product in the integrand, we're going to need the integration by parts. So I'm going to let u equal to t, and I'm going to let the dv equal to e to the minus st dt. Okay, so integration by parts says that the integral of u dv, which is what we have with this substitution, is equal to uv minus the integral of v du. So we need to find du, which will be simply just 1 dt, and then we have to find v, which will be minus 1 over s e to the minus st. Now making that substitution, this integral becomes uv, so minus 1 over s t e to the minus st minus the integral of v du. Now I'm going to rewrite this as 1 over e to the st. Okay, we're assuming the t is greater than 0. The s, as long as the s is positive, we know that this value will go towards 0. Well, we know this would, but we have this t here we have to also deal with. So we'll get to that in a minute. So now I have a plus the integral of 1 over s e to the minus st. And I'm going to go ahead and integrate that before I try to evaluate. This will all be evaluated from 0 to b after I finish the integration. Okay, e to the minus st, the s is a constant, so this is just going to be minus 1 over s squared e to the minus st. Okay, let's evaluate at b. We're putting that value in for the t's. And then minus 0 plugged in for the t's. So the first term will be 0, and we'll have minus 1 over s squared e to the 0, which is just minus 1 over s squared. Okay, so we have in this first expression, we have a minus 1 over s times b over e to the sb. I'm going to go ahead and split this up into multiple integrals. Minus the limit of 1 over s squared e to the minus sb, that's 1 over e to the sb. And then here we're going to have a plus 1 over s squared, which isn't affected by the b approaching infinity. So this will be plus 1 over s squared. So the next thing we need to do is figure out what are these two limits. Okay, now this one, as b goes to infinity, this expression is getting larger and larger, assuming that the s is positive. So again, s must be greater than 0 for this limit to exist. And this then will go towards 0. This one's not quite as obvious because you have both the b and the e to the sb both approaching infinity. So if you were trying to evaluate the expression as b is getting larger and larger, you see that the numerator is approaching infinity and the denominator is approaching infinity. This is called an infinity over infinity indeterminate form. So to evaluate that limit, we apply L'Hopital's rule. S. Okay, so take the derivative of the top, which will be just 1. The derivative of the bottom will be s e to the sb. Now let b go to infinity. The denominator will approach infinity, assuming the s is positive, which means the limit will come out to be 0. So this one also approaches 0. If you remember from calculus 1 and 2, where you talked about growth rates a little bit, e to the power, e to the t grows faster than just t. And that's exactly what's happening here. So that limit would approach 0 then. Okay, so what do we get? We get 1 over s squared for the value of the limit. That was the Laplace transform of the function t. Okay, so we now know that the Laplace transform of 1 is 1 over s, and the Laplace transform of t will be 1 over s squared. Now this will extend. We'll see in a minute that Laplace transform of t to a power is actually n factorial over s to the n plus 1. So the bottom will be s to 1 larger power, and the numerator is the power factorial. And you can see it would work in this situation where the t had a power of 1. It'd be 1 factorial over s to 1 larger power. Even in this case, if you thought of this as a t to the 0, we would have 0 factorial over t to 1 or s to 1 larger power, which would be s to the 1. 0 factorial by definition is just 1. So this is the general rule for polynomial terms. Okay, now let's look at the Laplace transform for the exponential function. So the Laplace transform of e to the at will be the integral from 0 to infinity. E to the minus st is the kernel, times e to the at is the function, the f of t. Now we can combine the two exponential functions. That's just e to the minus s minus a times t. Okay, and now remember the integral of an exponential function, e to the at is just 1 over a times e to the at. So this becomes negative 1 over s minus a e to the minus s minus a t. And we want to evaluate that from 0 to infinity. Okay, once again, as long as this exponent is negative, we know that this function will go to 0 as the t goes to infinity. So evaluating As t goes to infinity, we'll get 0, and then minus the negative 1 over s minus a, and then e to the 0, which comes out to be just 1 over s minus a. So the Laplace transform of e to the at is 1 over s minus a. And notice, this will exist, this integral will exist. This term will go to 0 as long as the s minus a is greater than 0. So our s does need to be greater than or equal to a for this integral to exist. Okay, so now this is the general rule for any exponential. So if we were trying to find the Laplace transform of e to the 5t, it would just be 1 over s minus 5. Okay, so now let's look at one of the trig functions. I want the Laplace transform of sine of b times t. That'll be the integral from 0 to infinity, e to the minus st times the sine of bt. Okay, now we have a product, and to integrate the product, we're going to need u substitution. So I'm going to let u equal sine of bt, the dv, e to the minus st. Now you probably could go either way on that one. I'm just using the acronym LIATE, which logarithms, inverse functions, algebraic expressions, things like x squared, trig functions. So this is the order to choose u in the integration by parts. And then exponential is the last. So here's integration by parts. Okay, now we need to find du, which will be b times cosine of bt, and then our v will be negative 1 over s e to the minus st. Okay, so integration by parts says that if we have, here's our u and our dv, the integral will be u times v minus the integral of v du. So we'll have sine of bt times negative 1 over s e to the minus st minus the integral of negative 1 over s e to the minus st times b cosine of bt. Go ahead and pull that b out as well. Okay, once again we have a product. These are different functions, so I'm going to use integration by parts once again. So I'm going to let this be my u and this be my dv. Minus negative 1 over s e to the minus st, the v, and then the du. And we still need to evaluate the right side from 0 to infinity. And I'll do that in a little bit. And this left side is just the Laplace transform of bt. Okay, let me clean this up a little bit. I'm going to distribute this b over s through as well. bunches of minuses in there. So ultimately it'll be a minus b over s squared. I'm going to go ahead and pull this 1 over s out in addition to this b over s. Whoops, I have another b here as well. So let me bring, that'll be a b squared out in front. Okay, so now all this is evaluated from 0 to infinity. So those in the integral, and then this needs to be evaluated, and this needs to be evaluated. Okay, now we've gone in circles. You'll notice that we have the same function here that we started with. Okay, that is just the Laplace transform of sine of bt. So I'm going to replace this with the Laplace transform of sine of bt. I've got a minus b squared over s squared in front of it. And now let me go ahead and evaluate this integral. I've got sine of bt, which I know is bound between -1 and 1. So it's less than or equal to 1. And we have this e to the minus st that as long as the s is positive, that's going to have a negative exponent. So as t is going to infinity, this function will go to 0. Okay? So this whole thing will go to 0 as t is approaching infinity. So then I'll have a negative, so I evaluate as t went to infinity, and then I have a minus -1 over s sine of 0 e to the 0. So I'm evaluating now at the 0. And then same thing for the second term. I've got, as t is going to infinity, this expression will go to 0, and this function is bound by 1. So this whole expression will go to 0 as t goes to infinity. But now I need to evaluate it at the 0 below. So I'm going to have a minus the negative b over s squared times cosine of 0 e to the 0. Okay, so now I've got this Laplace transform on this side and this side, so I'm going to move them both to the left side so that I can combine them. I'm going to have Laplace transform of sine of bt sine of 0 is 0, so this term is 0. Cosine of 0 is 1, and then this is 1. So we end up with only b over s squared on the right side. Okay, so now on the left, I'm going to factor out the Laplace transform of sine of bt, and I'm going to get 1 plus b squared over s squared. And so now, since our ultimate goal was to solve for this, I just need to divide by this expression. To simplify, I'm going to multiply the numerator and the denominator by s squared, which is the common denominator, and I would have b remaining on the top. I'm going to have s squared plus b squared on the bottom. So the Laplace transform for sine of bt is b over s squared plus b squared. So if I wanted to do an example, let's say I want to find the Laplace transform of sine of 2t. The b would be 2 here. So we're going to have 2 over s squared plus 2 squared. So 2 over s squared plus 4. It's the sine of 2t. Okay, now let's look at the Laplace transform of a piecewise function. So we have, by definition, the Laplace transform of the function f is the integral of e to the minus st times the function f from 0 to infinity. Now, since the function's given as a piecewise function, we need to break the interval that the limits of integration are over from 0 to 5, from 5 to 10, and then from 10 to infinity. So this will be equivalent to 0 to 5 e to the minus st times 2, since over that interval the function's definition is 2, plus from 5 to 10 we'll have e to the minus st times 0, and then from the interval from 10 to infinity we'll have the function e to the 4t. Okay, so integrating, we have minus, I'll pull the 2 out, and then it's minus 1 over s, so it's minus 2 over s e to the minus st, and that's evaluated from 0 to 5. This integral is 0, so we'd have a constant, and when you evaluated it at 10 and then at 5, it's going to be 0, so this whole thing is just 0. And then this one, we'll combine that to make it e to the minus s minus 4t, and that's from 10 to infinity. Okay, so evaluating at 5, we have minus 2 over s e to the minus 5s minus a negative 2 over s e to the 0. So that's the first integral. And then we have plus negative 1 over s minus 4 e to the minus s minus 4t. Okay, so now in this second integral, we will be evaluating as t goes to infinity. And so we're assuming that the s is greater than or equal to 4. Okay, for this function, the t is greater than 10, but for this to exist, the s must be greater than or equal to 4. So as t goes to infinity, this term will be positive, which means this exponent would be negative. So we know this term will go to 0 as t goes to infinity. And so now we'll have a minus a negative 1 over s minus 4 e to the minus s minus 4 times 10. Just evaluating it at 10. And see, over here I've got minus 2 over s e to the minus 5s plus 2 over s. Okay, and then if I want to change these, I can just make it a plus. So this is the Laplace transform for this piecewise function. Okay, not a lot I can do with that. That's about as simplified as we can have since all the exponents are different. Okay. One thing to point out is s does need to be greater than 4 or this won't exist here. So let me get rid of that. It should be for s greater than 4. And if you wanted to write it a little differently, you could say minus 2 e to the minus 5s. This is a function of s plus 2 over s. So when you have a piecewise function, just break it up into the intervals where the piecewise function is broken. Okay, one of the important properties that a Laplace transform has is called linearity. Okay, that means that the transform L is a linear operator. Okay, so what that means is that if we took two functions and you wanted to find the Laplace transform of the sum of the two functions, that would be equivalent to taking the sum of the Laplace transform of the two functions. Okay? It also means that if you took the Laplace transform of a constant times a function, it's equivalent to the constant times the Laplace transform of the function. So let me show you how that works. If we wanted to show that the Laplace transform, I'm just going to use f and g, f plus g is the Laplace transform for f plus the Laplace transform from g, we'd start with the definition of the Laplace transform for the function f plus g, which is the integral from 0 to infinity e to the minus st times f of t plus g of t. Okay? That is f plus g of t is f of t plus g of t. Now we know that integrals have the same property, so that we can break this up to be 0 to infinity e to the minus st times f of t, and then plus another integral 0 to infinity e to the minus st times g of t, which this is just the Laplace transform for the f, and this is the Laplace transform for the g. So that's our function, and we're evaluating t, the function of t. Okay, so that's the first property. Let's be consistent here. That's the first part of being linear. The next part is to show that a constant times a function will be the constant times the Laplace transform of that function. So by definition, from 0 to infinity e to the minus st, I place this function in, so times c f of t. But we know that this is a constant, and we can factor constants out of integrals. And this is just the Laplace transform of the function f of t. So we've shown these two properties hold. Putting that all together, that means that if you had the Laplace transform of a constant c1 times f plus c2 times g, so constant times f plus a constant times g, that would be equivalent to c1 times the Laplace transform of f plus c2 times the Laplace transform of g. So that's another way that they often state the linearity property. So let's see if we can apply this. Okay, so we know how to get the Laplace transform for the basic functions, 1, t, t to the n, any power of t. We also know how to get the Laplace transform for exponential function, the e to the at, and a sine of bt. So if we have any sums and constant products of any of those functions, we can also get the Laplace transform using the linearity property. So I want the Laplace transform of 11 plus 5e to the 4t minus 6 sine of 2t. So using the fact that it's linear, this is equal to Laplace transform of 11 plus the Laplace transform of 5e to the 4t plus the Laplace transform of negative 6 sine of 2t. That's just using the sum property. But 11, I don't know the Laplace transform of 11, but I know that's 11 times 1. So that's the 11 times the Laplace transform of 1 plus 5 times the Laplace transform of e to the 4t minus 6 times the Laplace transform of sine of 2t. Laplace transform of 1 is 1 over s. E to the 4t is 1 over s minus 4. And Laplace transform of sine of 2t would be the b, 2 over s squared plus the 2 squared. So we've got 11 over s plus 5 over s minus 4 minus 12 over s squared plus 4. And that's the Laplace transform for that function. Now we want to look at when the Laplace transform will exist. So the first thing we need to do is to look at a definition. A function f of t on an interval is said to have a jump discontinuity at a point t naught if the function is discontinuous at t naught, but the one-sided limits as t approaches t naught from the left and t approaches t naught from the right both exist as finite numbers. Okay? A function f of t is said to be piecewise continuous on a finite interval if f of t is continuous at every point in the interval except possibly for a finite number of points where there's a jump discontinuity. So a function is said to be piecewise continuous on the interval from 0 to infinity. So here we were talking about a finite interval. Here we're talking about 0 to infinity if f of t is piecewise continuous on 0 to n for any n greater than 0. So you can let n be anything, so as n gets larger and larger, we would say it was piecewise continuous from 0 to infinity as well. Okay, so let's look at an example. What does this mean? I want to show that this function is piecewise continuous. To be piecewise continuous, it can only have a finite number of places in the interval where it's discontinuous where there's a jump discontinuity. Okay, so looking at the graph here, we see that from 0 to 1, where the function, that says 1 there, the graph says 2. When t is 0 to, this should be 5, and this should be 10. The graph's just not quite correct. Okay, so from 0 to 5, we see that the function is defined to have the value of 2. Well, that's not even the right function. Okay, that looks more like the graph of y equal t, but since that's really a 5, they don't have the right function here. So this should be, see up here it looks like it's 2 over the interval from 5 to 10, and then the last one looks like it might, it's close, except it shouldn't be going through where f of t is never 0, so it should be more up higher than that. So that's not quite the right function. Let's just ignore the function here and look at the graph. So the function has a finite number of places it's discontinuous at t equal to 1 and at t equal 2, because clearly this line is continuous anywhere between 0 and 1, just not at t equal 1. And then this line is continuous on the whole interval 1 to 2, it's just not at the endpoints. And then this one would be continuous from 2 on. Okay? So the only two discontinuities are t equal 1 and t equal 2. So is there a jump discontinuity at those two places where it's not continuous? Well, a jump discontinuity means that it's discontinuous at that point, but that the limit from each side, so the limit of the function as t approaches 1 from the left side must exist, and the limit as t approaches 1 from the right side has to exist. So what is the limit as t approaches 1 from the left side? That means we're coming at 1 from this side. The function's values for those points are on this line, and they're getting closer and closer to the y value of 1. Well, approaching 1 from the right side would be coming this way, and the points for these t values are up on this line, and what those function values are approaching would be 2. Give the y value. Okay, so that means that at t equal 1 there is a jump discontinuity, since those two left and right limits exist. Okay, so now let's look at t equal 2. T equal 2, we need to look at the limit as t approaches 2 from the left and as t approaches 2 from the right. Okay, as t approaches 2 from the left, we would be approaching 2 from this direction. That means we're looking at values of the function up here, and they're getting closer and closer to 2 from the left side. From the right side, we would be getting close to t equal 2 from this way, with the function values corresponding to those t's are up here, and those values are getting close to the y equal to 0, so that limit is 0. So these both exist, so that means that t equal to 2 is also a jump discontinuity. And since we have a finite number of jump discontinuities in the interval from 0 to 3, so a finite number of jump discontinuities. In the interval 0 to 3, and that implies that f is piecewise continuous. refresh your memory on the definition. A function is piecewise continuous on a finite interval if it's continuous at every point except possibly for a finite number of places where there is a jump discontinuity. So we have shown that. Okay, so in contrast to that, let's look at a function f of t equal to 1 over t, which is this reciprocal function. It is not piecewise continuous, and the reason it's not is because there's a value. So if you take any interval that contains the origin, so let's take negative 5 to 5. Any interval that contains t equal to 0, at 0 we see a discontinuity, but it's not a jump discontinuity because the limit as t approaches 0 from the left is actually negative infinity, and the limit of the function as t approaches 0 from the right is actually positive infinity. So those limits do not exist. They're not finite values, so that means that there is not a jump discontinuity. It's an infinite jump. Okay. Now, it would be piecewise continuous for any interval that did not contain 0. Okay, so now we're trying to show when we're going to have, which functions will have a Laplace transform, when it's going to exist. Okay, a function that's piecewise continuous on a finite interval is not necessarily integrable over that interval. However, piecewise continuity is not enough to guarantee the existence of the Laplace transform. So what we have to consider is how fast that function's growing as t is getting larger. So the Laplace transform of a piecewise continuous function does exist, provided the function does not grow faster than an exponential function. Okay, so the way we state that is we use a term called exponential order. A function said to be exponential order alpha if there's a positive constant t in m so that f of t is less than or equal to m times e to the alpha t for all t greater than or equal to 0. Okay, what that really means is that any function that's bound above by some exponential function, it can have any constant multiplied by it. So this is just taking the absolute value of the function. So let's look at a couple of examples. So let's look at the function y equal to t. Okay, so this is f of t equal to t. Is there an exponential function that's always larger than that function? So now if you think about what the exponential functions we know, you know what y equal e to the t would look like. It looks like this. This function is less than or equal to e to the t for any t greater than or equal to, it doesn't matter if it's always, as long as from some point further out, it's always less than or, it's always below. That would mean it was of exponential order. So in this case, t is, the absolute value of t is less than or equal to just the function e to the t. So if alpha here would be the 1, the m we can use as 1, and so that function is bound above by the function e to the t. Another example, let's look at the sine function or cosine function. We've already seen that those Laplace transforms exist. Is there an exponential function that will always be larger than that? Well, now we know that if we looked at y equal e to the x, it might actually, I know the highest point here is 1, and this one's at 1, so it's always larger than 1 once your, t is greater than or equal to 0. So this function, just y equal e to the t, is greater than or equal to the sine function. Okay, so we would say sine of t less than or equal to, and if we weren't sure about that one, we could take any multiple of the e to the t. They allow you to pick a multiple of the e to the t. So, but I know it's just e to the t as well. Okay, so that means sine of t and t are of exponential order because they're bound above by some exponential function, which means what the theorem says here is that f of t is piecewise continuous. If it's piecewise continuous and of exponential order, then the Laplace transform will exist. Okay, so that's just how we know it exists, is whether it's of exponential order and it's piecewise continuous. That meaning it has a finite number of jump discontinuities in the interval. Okay, now we have a table that gives some of the Laplace transforms for elementary functions. There, you'll find these functions when we're solving some of the differential equations and that have the constant coefficients using the Laplace transform method. Okay, so we've already shown the Laplace transform of 1 was just 1 over s. The Laplace transform we saw of t was 1 over s squared. In general, the Laplace transform of t to the n was n factorial over s to the n plus 1. Okay, and so that's this one and this one, which of course the first two, follow this pattern as well. The Laplace transform of e to the at is 1 over s minus a. Laplace transform of sine of bt is b over s squared plus b squared. We didn't show it, but you could get it by using the definition. The Laplace transform of cosine of bt is s over s squared plus b squared. So we'll use that one as well. These others we're going to get to in the next section. They're actually a result of another property. When you have a product of e to a power times one of the other functions, see here's e to the at, here's e to the at, e to the at, times the t to the n. So we have the t to the n that we had above here. We have the sine of bt that we already had, the cosine of bt. They're not new rules. When you're multiplying by an exponential, you'll take the rule for this function and just apply a shift. So if this is e to the at, that means the shift is going to be s minus a. So take the rule for the cosine, which was here, and just replace all the s's with s minus a. So we have the s minus a here, and we have the s minus a here. Likewise, this one. The shift will be s minus a, so take all the s's in the sine of bt, which were here, just the s's, and replace it with s minus a. So we have the b over, here's the s minus a squared plus the b squared. Likewise here. Replace the s, take the t to the n, which is n factorial over s to the n plus 1, and do a shift of s minus a. So we're going to have the s minus a to the n plus 1. So we're using these same three rules, and we're just shifting them s minus a because of this multiplication of the exponential function. So you don't have to memorize those separately. That'll be a property that we get to that changes the other functions. Okay, we've seen how tedious using the definition of a Laplace transform can be since we have to evaluate the integral. In this section, we're going to establish some properties of the Laplace transform to make it easier to get those values without having to actually integrate. So I'm going to establish a property here. I want to find the Laplace transform of an exponential function e to the at times some function f of t. Okay, this is called an exponential multiple. Of the function f of t. Okay, so by the definition of the Laplace transform, this is the integral from 0 to infinity of e to the minus st times the function that we're interested in, which is e to the at f of t. Okay, now that comes out to be, this is e to the minus s minus a times t f of t. Let me write down what the Laplace transform of a function f of t is. Laplace transform of f of t is some function of s, which is, we'll call capital F of s, and that is whatever the integral of e to the minus st, it's not me, that's the smart board, times the f of t. notice here that f of s is this function. Notice where the s appears. It's the only place that the s appears in that function. So if we were to change this s here and here, it would be f of, s plus 1. F of s plus 1 would be the integral of e to the minus s plus 1 t f of t dt. So in this problem over here, I've got the same form that I have up here, except in place of the s, I have s minus a. So this will be f of s minus a. Okay, and that's all this is saying here. And if you want the Laplace transform of an exponential multiple of some function f of t, it's just going to be whatever the Laplace transform is of this f, which is what we call the capital F, shifted s minus a. Okay, so this essentially causes a shift in the Laplace transform of the function f of t. Okay, so let's find the Laplace transform of e to the alpha t sine of bt. Okay, so we see that this is an exponential multiple of sine of bt. So this is my function f of t. Find the capital F of s that's the Laplace transform of the f of t, which we know that the Laplace transform of sine of bt is equal to b over s squared plus b squared. So multiplying by this e to the alpha t, all it does is it shifts the function f. Instead of s here, it's going to shift it s minus a. So f of s minus a, which in this case is not a, it's alpha. I used alpha up there, is equal to, and now all you do is replace all the s's in this function, so it'll be b over s minus alpha squared plus b squared. Okay, so identify your f of t, it's what's being multiplied by the exponential function, and then find its Laplace transform, the capital F of s, by the rules that you've done before, and then shift it. Let's look at what a Laplace transform of a derivative of a function will be. So I want to find the Laplace transform of f prime of t. Okay, so by the definition, this will be the integral from 0 to infinity of e to the minus st times f prime of t. Using integration by parts, we'll have that u is equal to, now in this case I'm going to let u be the e to the minus st, and I'm going to let dv be the f prime of t dt. So du will be minus s e to the minus st, and v then would be the integral, which will be just f of t. So using integration by parts, this integral is u times v, so that's e to the minus st times f of t minus the integral of v du, which will be a plus the integral of, we'll have an s e to the minus st times f of t. Okay. Now this is just the Laplace transform of f of t. So we've got e to the minus st, right, 0 to infinity, and this one needs to be evaluated 0 to infinity. F of t from 0 to infinity plus s times the Laplace transform of the f of t. So we can find the Laplace transform of f prime of t in terms of the Laplace transform of f of t. Okay, so now let's finish this up. Evaluating this, as t goes to infinity, this will go to 0, and then we'll have a minus e to the 0 f of 0, evaluating it at 0. Okay, e to the 0, 0, so what this comes out to be then is s times the Laplace transform of f of t minus just f of 0. That's the Laplace transform of f prime of t. So the nice thing about that is it takes a derivative. If we take the Laplace transform of a derivative, we would get s times just the Laplace transform for the original function. So what we're going to use this for is we're going to take Laplace transforms of differential equations, and they're going to convert the derivatives to the original functions in the equation. So then we're just going to have an equation to solve algebraically. So that's going to be the advantage of this. Now let's look at one more. Let me go ahead and look at f double prime just so we can see a pattern. Laplace transform of f double prime of t by definition. Okay, integration by parts. Okay, so this becomes e to the minus st f prime of t evaluated from 0 to infinity minus the negative, so it'll be plus s times the integral of e to the minus st f prime of t. Okay, now we've already found this. This is the Laplace transform of f prime, which we know is just s times the Laplace transform of f of t minus f of 0. And now evaluating this, as t goes to infinity, this will go to 0 because of this e to the minus st term, and then evaluate at 0, so we'll have minus e to the 0 f prime of 0. Okay, so my first term that I'll put will be s squared Laplace transform of f of t minus s times f of 0, and then minus e to 0 is 1, so that's f prime of 0. Again, we just took a second order derivative and turned it into an equation with just the Laplace transform of the function f. Okay? So those are the two equations that we'll be using the most often. In general, if you take a higher order derivative, the Laplace transform of the nth order derivative will be s to the n times the Laplace transform of the f. So whatever this order derivative is matches the power of the s, minus, and then you're going to go down 1 on the power of s at each point. So here was an s squared, here was an s, and then they were gone. And then you start with the Laplace transform of f, and then that next term will be the next lower power of s, but times the f evaluated at 0, and then you keep going all the way down, and each time your derivatives will be going up one order. So here was f of 0, you'll have f prime of 0, the next one would be f double prime of 0 if you had another term, but each time the powers of s are going down. So if I wanted to write down what the form would be for the Laplace transform of f triple prime, it would be s to the third, matches the order of the derivative, times the Laplace transform of the f, minus s squared times f of 0, minus s times f prime of 0, minus, now my s's are gone, they've gone down by 1, but I go up an order of the derivative, and each time it's evaluated at 0. So the time that Laplace transforms will be helpful is when we have differential equations with initial conditions given at the x or t equal to 0. Now I'm going to use the result that we just found, that Laplace transform of f prime of t is equal to s times the Laplace transform of f of t minus f of 0 to find the Laplace transform of cosine of bt. Okay, so we know what the Laplace transform of sine of bt is. So I'm going to let f of t be sine of bt. Okay. F prime of t is b times cosine of bt. So by this result, the Laplace transform of f prime, which is b cosine of bt, is equal to s times the Laplace transform of the f, which is sine of bt, minus f of 0. But if this is my f of 0 is equal to sine of 0, which is just 0. So that means that the Laplace transform, now let me go ahead and pull this b out, since I know that the Laplace transform is linear, is equal to s times the Laplace transform of sine of bt plus 0. We know the Laplace transform of sine of bt is equal to s times b over s squared plus b squared. Now dividing both sides by b, we get the Laplace transform of cosine of bt is equal to s over s squared plus b squared. Okay, and you could also get that from the definition, but this saves you from having to go through the integration. Okay, another result. We're going to use the same rule for the derivative. I want to define a new function here. I'm going to call it g of x, or g of t, will be the function from 0 to t of f of tau d tau. I'm changing the variable of integration because I have an upper limit that's t, so I can't use the letter t. Okay, this means then that g prime of t is just the derivative of that integral. If you remember, the fundamental theorem of calculus from Calculus 1 says the derivative of an integral from 0 to t is just the function here evaluated at that upper limit. So it's just f of t. Okay, so now I'm going to apply the previous theorem up here to g of t. So I know that the Laplace transform of g prime is equal to s times the Laplace transform of g of t minus g of 0. I'm just using this property, but using the function g. Well, the Laplace transform of g prime, well, g prime is just f of t from here. G of t is the integral from 0 to t of f of tau from right here. G of 0, let's see, if we evaluated this function at 0, g of 0 would mean we were wanting the integral from 0 to 0. I'm replacing the t's here and here with 0, which is just 0. Okay, so what that tells me then is that the Laplace transform of the integral from 0 to t f of tau is equal to 1 over s times the Laplace transform of f of t. Now, one more little sleight of hand here. I'm going to use this result that we just showed here, and I'm going to note that the sine of bt is just equal to the integral from 0 to t of b times cosine of bt. Right? If you integrated cosine of bt, you would get 1 over b sine of bt, and the b's would cancel. So this is a true statement. So if I took the Laplace transform of this, it would be the Laplace transform of this, but by the result up here, I'm comparing to this, my function would be the f of tau here would be this cosine of, let's see, I need to change that to tau, b tau, d tau. Okay, so this, comparing it to this right here, the function f that's evaluated at tau would be cosine of b tau. I could use the f too. So this is f of tau from the theorem, but that's equal to this, which is 1 over s times the Laplace transform of the function f, which is b cosine of bt, and then it'll be a function of s. We don't need to put that at last s there. Okay, so Laplace transform of b cosine of bt, I can bring the b out, so this will be b over s times the Laplace transform of cosine of bt. This just says the Laplace transform of sine of bt is b over s times the Laplace transform of cosine of bt, which we know that's a true statement. So if you took this and multiplied it by b over s, you do get the Laplace transform of bt. And now we're going to look at how to use the Laplace transforms to solve a differential equation given initial conditions at t equal to 0. Okay, the function that we're going to be looking for in this differential equation is called y, and it's a function of t. We can see the t's in the equation. So I'm going to use the notation Laplace transform of y of t, which is the function that we're looking for, we're going to call capital Y of s, because we know it's got to be a function of s. Okay, so now, take the Laplace transform of both sides of the differential equation. We're going to have the Laplace transform of y double prime minus y equal the Laplace transform of negative t. Now we have the linearity property that says that this is the Laplace transform of y double prime minus the Laplace transform of y equal negative the Laplace transform of t. Well, by a previous theorem, we know how to find the Laplace transform of a derivative. It's going to be, since it's a second derivative, it's going to be s squared times the Laplace transform of y minus s times y of 0 minus y prime of 0. So all of this was the Laplace transform of y double prime. And then we have minus our Laplace transform of y. And I know the Laplace transform of t is just 1 over s squared. Okay, now I'm going to replace the Laplace transform of y with capital Y of s. I also know that y of 0 is just 0, and y prime of 0 is just 1. Now our goal here is to solve for y of s. So you apply the Laplace transform to both sides and then solve for y of s. Okay, so I'm going to group the y of s terms together and factor out that expression. So I'm going to have s squared minus 1. This is 0. This is 1. I'm going to take it to the other side. Now, adding the two terms, getting the common denominator on the right, I'm going to have s squared minus 1 over s squared. Okay, now we're just going to divide both sides by s squared minus 1. We get that y of s has to be just 1 over s squared. Okay, remember, y of s is the Laplace transform of y, the function that we're looking for. Here we can just guess, based on what we've just been doing, what function, little y, has the Laplace transform 1 over s squared. And it's just t. So t is our solution to this differential equation. And if we checked it, the second derivative would be 0 minus t is the y equal negative t, and that's true. If you evaluate it at y of 0, you get 0. If you take the derivative, which is 1, and you get 1. So there's our solution. Okay, we saw in the last example that if you apply the Laplace transform and solve for capital Y of s, which is the Laplace transform for the function that you're looking for, you might have to then figure out, well, what function had that Laplace transform? So we're going to introduce an idea of an inverse Laplace transform. So given a function capital F of s, if there's a function little f of t that's continuous on the interval and satisfies the Laplace transform, the little f is capital F, then we say that the little f is the inverse Laplace transform of capital F, and use the notation little f is the inverse Laplace transform of the capital F. So let's find inverse Laplace transforms of these given functions. So capital F of s is 2 over s squared, or 2 over s cubed. So I want to find what function had the Laplace transform of 2 over s cubed. Well, if you recall, the Laplace transform of t to the n was n factorial over s to the n plus 1. You can guess here that if this exponent is a 3, then that means that the n would have to be 2. Okay, so if we were trying to find the Laplace transform of t squared, that would be 2 factorial over s to the third, and that's exactly what we have. So the inverse Laplace transform of 2 over s squared, s cubed, sorry, is equal to just t squared. Okay, looking at this one, thinking about the formulas that you already have, we had a formula that said the Laplace transform of sine of bt was equal to b over s squared plus b squared. We also had another one that the Laplace transform of cosine of bt was s over s squared plus b squared. Okay, so our basic ones were this one, this one, this one, and then we had the Laplace transform for an exponential, which is 1 over s minus a. Then we saw that if you had a exponential multiple of another function, so something like e to the at times another function, you would just find the Laplace transform for the little f and then shift it s minus a. So that one might come into play as well. Okay, so we'll use these formulas to find the inverse Laplace transforms. So now, which one of those matches this one, is closest to that one? Well, you see a constant on top and an s squared plus a 9, so it looks the closest to this one. So let's look at what would the b have to be for this problem. Well, because of the b on top and the b, look at the bottom first. We have an s squared plus 9, so that could be written as 3 over s squared plus 3 squared, and we just happen to have that 3 on the top. So this one matches exactly that formula where the b is equal to 3. So the inverse Laplace transform of 3 over s squared plus 9 is simply sine of 3t. Okay, this last one's not so obvious. We see a square in the bottom, but it doesn't fit the sum of squares like the sine and the cosine do. But what we can do is we can complete the square on the denominator. This is equivalent to s squared minus 2s plus 1. Now if I take half of this middle term, which is the negative 1, the half of the coefficient, and square it, I get the plus 1. That's going to factor to be a perfect square. But I put a plus 1, so I have the 5 already there. I need to subtract the 1 as well to make it all the same as what I started with. So all I did was I completed the square using these first two terms to determine what to add and subtract from the bottom. Okay, so I've got s minus 1 squared plus 4, and then I've got an s minus 1 on the top. Well, that looks a whole lot like this formula, except we've got s minus 1 where the s's belong. So if I think of this as a function f of s minus 1, remember that we had this policy that this property that if you had a exponential multiple of some function, you just did a shift of it. So if I replaced the s minus 1 here and here with just an s, and look at what would the function have been, the inverse have been for that, s over s squared plus 4, well, that one would have been this, where the b was equal to 2. Okay, so I know that the Laplace transform of cosine of 2t would have been just s over s squared plus 4, and that's exactly what this is, except it shifted s minus 1. So to cause a shift, you take this function and you multiply it by e to the, since the shift is s minus 1, you'll multiply it by e to the 1t. So the inverse Laplace transform of s minus 1 over s squared minus 2s plus 5 will be e to the t times cosine of 2t. So if you want to verify that, let's just apply this rule to this function now. When you see an exponential times a function, take the Laplace transform for the function, which we know to be s over s squared plus 4, and now shift it as a result of this at. The 1 here is what causes the shift of s minus 1. It's going to be s minus 1 over s minus 1 squared plus the 4. And that's exactly what we had here. And if you distribute out the bottom, you get this back. Okay, so that's the inverse Laplace transform. Let's apply it in some other cases. Now, we also have a linearity property for the inverse transform, just like for the Laplace transform. So if you have an inverse Laplace transform of a sum of two functions, you can just take the inverse of each one of those separately and add them. Or if you have a constant times a function and want the inverse Laplace transform, just take the constant times the inverse of the other function. So when I see this, I know that this is equal to 5 times the inverse Laplace transform of 1 over s minus 6 minus 6 times the Laplace transform, the inverse Laplace transform of s over s squared plus 9. I'm just breaking up the sum and pulling constants out, plus 3 times the inverse Laplace transform of 1 over 2s squared plus 8s plus 10. Now that one looks like it's going to cause a little bit of a problem. These first two are simple enough. This is 5 times. I recognize the 1 over s minus 6 to be e to the 6t, because the Laplace transform of e to the 6t is 1 over s minus 6. And I have minus 6 times the s over s squared plus 9 is a cosine. So it's cosine of 3t. So now this is the one that's the most difficult. It doesn't fit any of the, it's not the 1 over s minus a like the exponential would be. It looks like the sine or cosine, but we have a much more complicated denominator. So we're going to need to complete the square, and to do that, I can't have this 2 in front. So I'm going to take a 2 out of everything. So I'm going to rewrite this as 1 over 2 times s squared plus 4s plus 5. And so now that's just going to be 1/2 times the fraction 1 over s squared plus 4s plus 5. So what I'm doing then is I'm going to take this and rewrite this as 3 over the 2 times the inverse Laplace transform of 1 over s squared plus 4s plus 5. So I'm pulling the 1/2 out to leave me a 1 down in front of the s squared so that I can complete the square. So continuing with this, I've got 5e to the 6t minus 6 cosine of 3t plus 3/2. Now completing the square, I'm going to have s squared plus 4s. I need a plus 4 to make this a perfect square, half of the 4 in front of the s, and square it. Plus 5, I just added 4, so I've got to subtract a 4 to make it balance out. Okay? Factor at the bottom. I now have 1 over s plus 2 squared plus 1. Now recall the formula. It has a constant on top, so I'm going to look at the Laplace transform of the sine function. Cosine has an s on top. The sine function, let's see, down here I've got a 1, so I'm going to look at just a 1t. And I know that that would be 1, it's whatever the b is, which is 1, over s squared plus the 1. And that's very similar to this, except I've got a shift. Instead of the s, I'm replacing it with an s plus 2. So the shift results in that exponential multiple of this function. So I know I've got the function sine of just a 1t because of the 1 on the top and the plus the 1. And then since it's an s plus 2, that's a shift of negative 2, so that's negative 2t. Okay? And that is the inverse Laplace transform of this function that we started with. Let's look at a couple more. Think about the set of properties that you have. This one looks closest to the one that's a t to a power. We know the Laplace transform of t to a power is n factorial over s to the n plus 1. So what would the n have to be to get this power here? Well, the n would have to be 3. Okay, so now let's think. What would the Laplace transform of t to the third look like? Laplace transform of t to the third would be 3 factorial over s to the fourth, which is very similar to this except for the 3 factorial. So let me rewrite this another way. This is equal to 5 times the inverse Laplace transform of 1 over s plus 2 to the fourth. I'm not worried about that s plus 2. That's a shift, which at the end, once we figure out what function got the main form of it, we'll just multiply it by e to the minus 2t because the shift is s plus 2. So I've got the s to the fourth on the bottom. I need to get the 3 factorial on the top. So if I put a 3 factorial here to match this form, I need to also divide by 3 factorial, and I can do that on the outside since it's just a constant anyway. So thinking about this, I've got 5 over 6, which is 3 factorial, and now the inverse Laplace transform of 3 factorial over s plus 2 to the fourth. It matches this one exactly now, except instead of s, we're putting s plus 2, which means it's just an exponential multiple of this function. So we have 5/6 t cubed, and the exponential function, because it's s plus 2, is minus 2t. And this will be the function that has, whose Laplace transform is this. So you can always check your answers. Take the Laplace transform for this. If you want to check it, I'll go ahead and do that. If I want the Laplace transform of this, I know that's 5/6 times the Laplace transform of e to the minus 2t, t cubed. Okay, this is an exponential multiple of t cubed, so I get the rule for t cubed, which we know is 3 factorial over s to the fourth. And because of that exponential multiple, it's a shift of s plus 2. So the way we can write that is it's this function shifted s plus 2, which we can write it as 5/6 3 factorial over s plus 2 to the fourth. We're just evaluating that function at s plus 2. And now the 3 factorials would cancel, and you get 5 over s plus 2 to the fourth. Okay, now let's look at this last one. It's a little more complicated. We know we have the property that Laplace transform of sine of bt is b over s squared plus b squared. And we know we have Laplace transform of cosine of bt is s over s squared plus b squared. But we have an s and a constant added together on the top here. So what I need to do is I need to break this up into two fractions. Or before I do that, let me go ahead and worry about the denominator. I'm going to need to factor that because I don't have a sum of two squares, so I've got to complete the square on that one. So this one will be the inverse Laplace transform of s squared plus 2s plus 1, and then plus a 10 minus 1. So all I did was I added 1 and subtracted 1 to make this a perfect square. So I've got s plus 1 squared plus 9. Okay, now I've got an 3s plus 2, and I know if I'm going to have an s on the top, it's got to match whatever the s is here. So if I'm going to be shifting it by s plus 1, I've got to have an s plus 1 on the top where the s is. So I'm going to put an s plus 1 here and figure out how I can force the top to be something times the s plus 1 plus a constant. So I know I have to have a 3 in front of the s. Okay, now I've got to make these two the same though. I had an 3s plus 2 here. I need to make it match here. I have the 3s plus 3 right now. If I distribute the 3 through, to get the 2, I need to subtract a 1. And so now, if you check, it should be 3s plus 2 on the top. Okay, so the reason for that is I'm now going to break this up into two fractions. I'm going to split. I'm going to have a 3 times s plus 1 for the top of one of them. And then I'm going to have a minus 1 over s plus 1 squared plus 9 for the other one. All I'm doing is I'm splitting up this into two fractions, keeping the denominator, but splitting the numerator. It's just undoing a common denominator. And I did that so that I can get the s away from the constant on the top so that I can apply both of these two rules now. Okay, so now, the thing that's off on the top of this one is this 3. I don't want a 3 there if I'm looking at the Laplace transform of cosine. So I'm going to pull that 3 out in front. So that'll be s plus 1 over s plus 1 squared plus 9. And then minus the Laplace transform, the inverse Laplace transform of 1 over s plus 1 squared plus 9. We'll do those two separately. We need them separate because this one has an s on the top and this one doesn't. Okay, so now this one, the first one here, now matches the cosine where the s is replaced with s plus 1. Okay, so that means it's going to be an exponential multiple of whatever function this was. So we're going to have 3 times cosine. The b has to be 3 because of this 9, so 3t. And because it's a shift of, it's s plus 1, it's a shift minus t. So minus 1 is the coefficient of the t in that exponential function that's shifting. Okay, the second one now. This one matches this, except we don't have the right coefficient on the top, the constant on the top. If this is a 9, that means our b has to be 3. So I need to put a 3 up here, and I need to multiply by 1/3 in front. And so now it matches the sine rule, except we're replacing the s's with s plus 1. Again, that's just going to be a shift, an exponential shift. So I've got minus 1/3. The general pattern is the sine of 3t, and the exponential shift is e to the minus t. And that's your inverse Laplace transform of this function. So you might have to break it up into multiple fractions depending on which form it's closest to. You can only have an s on top of this one, not this one. Okay, now as we're finding inverse Laplace transforms for rational functions, we're going to find it's necessary sometimes to break the fractions up into smaller fractions. So there's a method called partial fraction decomposition that accomplishes that. First off, we're going to look at a rational function of the form P of S over Q of S, where P of S has a smaller degree than Q of S. So you have to have a proper fraction. If you don't, you're going to have to do long division first, so that then the remainder is a proper fraction, and then we'll decompose it. So this only works if the numerator is a smaller degree than the denominator. You'll have one extra step if it doesn't. Okay, so now there's going to be three cases here to know what the decomposition looks like, and it all depends on what the factors of Q of S are. So factor Q of S down to the lowest possible terms. We can factor it down to either linear factors or a quadratic factor, where the quadratic factor can't be reduced any further. So the example of a non-repeated linear factors means that you've got the denominator and its factors of the form like s minus 1 times s plus 3, so that each factor is linear, and that just means it has a degree 1. So this factor has a degree 1, this factor has degree 1, and these are not repeated, meaning I don't have a s minus 1 twice. Okay, the second case will be a repeated linear factors. That means that I've got something like an s minus 1 that occurs more than once, so maybe an s minus 1 squared or s plus 3 squared. So you've got some repeated linear factors. And then the last case will be when the factor is quadratic. And that means you've got something that doesn't reduce down to linear factors. So it might be something like an s squared plus 3, or perhaps a s squared plus 4s plus 1, something that doesn't factor further, but it is a quadratic factor. Now, depending on the form of the factors of Q of S will tell you what the form of the decomposition is going to look like. So first, let's look at when all factors of Q of S are non-repeated linear factors. So we know they're all of the form s minus r1, s minus r2, down to some s minus rn. So every factor is linear, and none of them repeat. The form that this fraction will be decomposed in will be fractions with those factors in each denominator, and the numerator in each one will be just a constant term. Okay? So that's the first decomposition we're going to look at, all linear factors in the denominator. Okay, so maybe we were given a problem finding the inverse Laplace transform of this. Well, it doesn't fit any of the rules that we've done in the past. We could handle a 1 over s plus 1, but not where you have all those factors in one fraction. So we need to first do a partial fraction decomposition on this, and notice each factor is not repeated. So we do have a proper fraction because the numerator here has degree 1. That's the biggest power of the s. And down here it's actually a degree 3. So the decomposition for that function, I'm just going to take 7s minus 1 and I know it can decompose into 3 fractions, each with one of these factors, s plus 1, s plus 2, and s minus 3. Because they're linear factors, the numerator is going to be just a constant term. So I don't want to use the subscript, so ABC. Okay, now to solve that, first multiply through by the common denominator, which is this s plus 1, s plus 2, s minus 3, and you get 7s minus 1 equal a times s plus 2, s minus 3, plus b times s plus 1, s minus 3, plus c times s plus 1 times s plus 2. Okay, now when they're linear factors, what you're going to need, you have 3 variables, a, b, and c you're trying to solve for. With the linear factors, you need 3 equations, and you're going to let s be each of the numbers that would make the denominator 0. So I'm going to choose s equal -1, s equal -2, and s equal 3 to get my 3 equations. And I'm just going to plug those into both sides of this equation. When I use -1, this first left side becomes -8. When I plug -1 into the right, I would get a times 1 times -4. This will become a 0 when I plug -1 in, and this becomes a 0. So everything else is just 0. So I get that negative 8 is equal to negative 4 times the a. So that means my a is just equal to positive 2. Okay, now s equal negative 2. Repeat the same thing. You're plugging it into both sides here. So it's going to be negative 15 on the left. When I plug negative 2 into this, it's 0, or into this, it's 0. So the only term over here that's going to not be 0 will be the middle one. So it's b times, I'm plugging negative 2 for s, so negative 1 times negative 5, which means that I have negative 15 equal to 5b, which means that the b is going to be negative 3. And then finally, s equal 3. Plugging on the left, I get 20, because I'll have 21 minus 1. On the right, this will be 0, this will be 0, so the third term is the only one that won't be 0, so it's c times 3 plus 1, 3 plus 2. So I have that 20 is equal to 20c. That means my c is equal to 1. So this decomposition then, with these values plugged in, I have inverse Laplace transform of 7s minus 1 over s plus 1, s plus 2, and s minus 3. That's the same thing as the inverse Laplace transform of the a, which is 2 over s plus 1, plus the b over s plus 2, plus the c over s minus 3, which is inverse Laplace 2 times the inverse Laplace transform of 1 over s plus 1, minus 3 times the inverse Laplace transform of 1 over s plus 2, plus the inverse Laplace transform of 1 over s minus 3. Now we have our simple fractions. This is 2 times e to the minus t minus 3 times e to the minus 2t plus e to the 3t. And there's the inverse Laplace transform of this fraction. Okay, now let's look at the next case. What if you have a repeated linear factor? Okay, so you have an s minus r in the denominator that appears more than one time. Okay, so if you have that situation, that one factor can't be just decomposed into a over s minus r. Instead, you have to have an s minus r to every power less than or equal to the m. So that one term will correspond to an a over s minus r plus a b over s minus r squared all the way up to whatever that power is that's on the s minus r. Okay, so now let's look at this example. Based on the function, the rational function that I'm given, I have a linear factor that's repeated, s minus 1's twice, and then s plus 3 is not repeated. So the form that I can decompose it into, I'll need one fraction with an s minus 1, but another fraction with an s minus 1 squared because of that repeated factor s minus 1. Now each one of these, though, because it's a linear factor, will still just have a constant on top. Okay, now I still have this factor that's not repeated, so I'll have another fraction with an s plus 3 on the bottom. So that's the form of the decomposition. First, get rid of the fractions by multiplying through by the common denominator, and you get this. Okay. We have three unknowns, a, b, and c. We need three equations to be able to solve for those uniquely. I'm going to choose s equal 1 and s equal negative 3 because those make those factors 0, but I'm going to need one more item, something easy, so I'll probably use s equal to 0. Okay, plugging in s equal 1 to both sides of the equation, I get 1 plus 9 plus 2 is 12. 1 into the first and last term will be 0, so I end up getting 4b. So that means b is equal to 3. S equal negative 3. On the left, I'm going to have 9 minus 27, so that's minus 18, plus 2, so minus 16. negative 3 on the right. The first two terms will be 0, and I get negative 4 squared, so that'll be 16c. That means my c is negative 1. And now just plug in s equal to 0 to get a third equation. So I'm going to get 2 on the left. I'm going to get negative 3a plus 3b plus c, because I've got negative 1 squared. Now plug in the values you've already found. We need to find a still. So 3 times the 3 that we already found for b, and the negative 1 for the c. So that means negative 3a is equal to, see, I have 8, move to the other side, will be a negative 6. So that means my a is equal to 2. So now, coming back to my problem, I want the inverse Laplace transform of this, which is equal to the inverse Laplace transform of this fraction that's equivalent, which will be 2 over s minus 1 plus 3 over s minus 1 squared plus negative 1 over s plus 3. Okay, use the linearity property. This is 2 times the inverse Laplace transform of 1 over s minus 1 plus 3 times the inverse Laplace transform of 1 over s minus 1 squared minus 1 times the inverse Laplace transform of 1 over s plus 3. Okay, this one's easy enough. That's just the exponential function to the t power. So 2e to the t, since the a is, I'm just using the property, Laplace transform of e to the at equal to 1 over s minus a. Now this one is a shift. I'm looking at the function 1 over s squared. If I can find the inverse Laplace transform of 1 over s squared, I'm just going to shift it by using an exponential multiple, which is s minus 1. Well, the inverse Laplace transform of 1 over s squared was just t. So this will be plus 3 times, t is the function that's going to be multiplied by e to the t. And then we have minus 1 times e to the minus 3t. Okay, so now let's look at, you probably would write this as 3t e to the t instead of, it's easier to read that way. Okay, so now we're going to look at the last case of having a quadratic factor. Okay, so let's say we have a quadratic factor, something that doesn't factor into linear factors. So something of this form. Okay, and it may not look like that. It may just be s squared plus 2s plus 5. Okay, the form of the decomposition, for every quadratic you have here that doesn't factor down to a linear factors, a product of linear factors, the numerator will be a linear term. Okay, so if you have s squared plus 2s plus 5, it doesn't factor any further. So my numerator for that factor would be as plus b. It's got to be something with an s to the first and a constant term. Okay, now if one of these factors appeared multiple times, we have to do the same thing that we did with the repeated linear factors. So let's say that we had this factor, s squared plus 2s plus 5 to the third power in the denominator, in that q of s. Then I would have to have one term that had s squared plus 2s plus 5. I would have to have another one with s squared plus 2s plus 5 to the second power. And I'd have to have a third term that had s squared plus 2s plus 5 to the third power. And each time I have to have that linear factor, so I'd have a cs plus d and an es plus f for that repeated quadratic factor. So now let's look at an example. Okay, here's one where we have two factors in the denominator. One of them is a quadratic that does not reduce further. You can't factor that. And the s plus 1. So the decomposition then will be of the form Now notice the numerator is degree smaller than the denominator. The denominator will be an s cubed if you multiplied it out. The numerator is an s squared for the largest power. Okay, so the form of our decomposition will be 1 fraction with s squared minus 2s plus 5. Because it's a quadratic, irreducible quadratic, we will have an as plus b in the numerator. And then the other factor, for the s plus 1, since that's a linear factor, we'll just have a constant. So now multiply through by the common denominator, you're going to end up with 2s squared plus 10s. And then we're going to have as plus b times s plus 1 plus c times s squared minus 2s plus 5. Now I'm going to show you an alternative way to just plugging in numbers. If we just plugged in numbers, we'd only have -1 that would be an easy one. Then we'd have to pick 2 more, and then we end up getting 3 equations with a, b, and c. Sometimes that's not the easiest way when you have these quadratic factors. So what I'm going to show you is just distributing out the right side, and then we're going to look at the like terms on both sides. So I have 2s squared plus 10s on the left, and I'm going to have as squared plus as plus bs plus b plus cs squared minus 2cs plus 5c. Now group them on the right based on the degree of the s. So I'm going to group the s squared terms together. I have an a s squared and I have a plus c. So factor out the s squared. I have a plus c as the coefficient of the s squared. Now let's look at the s terms. I have an as, I have a bs, and I have a minus 2cs. So factoring out the s, I have a plus b minus 2c. And now the constant terms. I have just a b plus 5c that don't have any s's. So now, for these two sides to be equal, their coefficients of the like terms have to be the same. So the s squared coefficient has to be the s squared coefficient. So I know 2 has to be a plus c. The s coefficient has to be the s coefficient on the right side. So I know that 10 has to be a plus b minus 2c. And then the constant term on the left doesn't exist, so it's 0. And on the right would be b plus 5c. So now we have 3 equations with 3 unknowns. To solve those, you have to eliminate the same variable from 2 different pairs. So let's see. I know I can take the first and third equation and eliminate the c. Let's just eliminate c. I'll use the first and third, and then I have to use the second one with one of the equations. So let's eliminate c by taking 2 pairs of equations that can eliminate the c. So eliminate c with these 2. I would need to multiply the first equation through by -5. So I'd have -10 equal to -5a minus 5c. That's from equation 1. And then this last equation, leave it the way it is, and then now just add the 2. I get -10 is equal to -5a plus b. Now I need to use the second equation with one of the others. I'm going to use the first equation because it doesn't have that 5 in front of the c. So I'm going to multiply the top one through by 2. And then take the second equation the way it is. So now adding these 2, I get that 14 is equal to 3a plus b. So now I've got this equation and this equation that both combined those 3 and now just has an a and a b in them. So now let's take these and we're going to eliminate a variable again. Those can easily eliminate the b just by subtracting them. So let me just take this equation, and I'm going to take -1 times this equation here. So it'll be 10 equal to 5a minus 5 minus b Just multiply them through by negative 1. And now add the equations. The b's go away. I get 8a equal to 24. So that means that my a is equal to 3. And now we're cruising here. We've got a is 3. I'll put a equal 3 up here. And I get that 14 is equal to 9 plus b. So that means b is 5. Yes. B is 5. And now we'll just go back to one of them that has a c. We can go back to this first one here. We know that 2 is equal to 3 plus c, so that means our c is negative 1. Okay, so now we've got our decomposition. This inverse Laplace transform is the same thing as the inverse Laplace transform of, and I'm taking this decomposition. The a was 3, so I've got 3s plus 5 over s squared minus 2s plus 5 plus negative 1 over s plus 1. Okay, so that's the inverse Laplace transform of 3s plus 5 over, I'm going to go ahead and factor complete the square on the bottom. That's s minus 1 squared plus 4. And then minus the inverse Laplace transform of 1 over s plus 1. Now, we've been here before. We need to have an s minus, we're going to split this into two fractions, but we have to have an s minus 1 on top to be able to use the cosine. So we're going to rewrite this as 3 times s minus 1. And then we have that plus 5, so I'm going to need a plus 8 to get the 5 still. And this one we know is just e to the minus t. Okay, now break this into two fractions. This is inverse Laplace transform of 3 times s minus 1 over s minus 1 squared plus 4 plus inverse Laplace transform of 8 over s minus 1 squared plus 4. Clean up the constants a little bit. I'm going to pull the 3 out. This will be the s minus 1 on top, the s minus 1 squared plus the 4 on bottom. I'm going to pull the 8 out. Actually, instead of, if I can pull the 8 out, but then I know I'm going to have a 2 on top because of this, it's going to be a sign, and it needs the k on top. So I'm just going to pull out a 4 and leave the 2 on top. And that way it'll be set up to do the inverse Laplace transform. Okay, so now this one, the first one, is just the cosine of 2t, but instead of the s's, it's replaced with s minus 1, which just means it's an exponential shift. So this will be 3 times cosine of 2t, I know the 2 because of the 4 on the bottom, and then the exponential shift is just e to the t. This one's also an exponential shift. We've got the s minus 1 in place of the s on the bottom, and it's set up to be the sign other than that. So it's going to be 4 times sine of 2t, and then the exponential shift of e to the t as well. And then we've still got our minus e to the minus t right here. And that should be it. Okay, now we're going to solve initial value problems using Laplace transforms. So first step is to take the Laplace transform of both sides of the equation. Then we're going to use the properties of Laplace transform to change the equation to an algebraic equation. Okay, you'll solve for the y of s, and then you'll find the inverse Laplace transform of that by either using tables, using partial fraction decompositions, in the table of basic properties that we've used to find that inverse. Okay, so step 1, take the Laplace transform of both sides. I'm going to use the linearity property, and the left side becomes the Laplace transform of y double prime minus 2 times the Laplace transform of y prime plus 5 times the Laplace transform of y is equal to minus 8 times the Laplace transform of e to the minus t. Now note that our initial conditions are given for t equal to 0, which is required for the Laplace transform. Okay, now using the property for the Laplace transform of a derivative, we know the Laplace transform of the second derivative will be s squared, the Laplace transform of y, minus s times y of 0, minus y prime of 0. This is all of this. And then minus 2 times the Laplace transform of the derivative. So that will be just s, the Laplace transform of y, minus y of 0. Okay. And then we have plus 5 times the Laplace transform of y. The Laplace transform of e to the minus t is 1 over s minus negative 1, so s plus 1. Okay, now on the left, I have a lot of terms that have, 3 terms that have the Laplace transform of y, which is y of s. Okay, so I'm going to group those. Okay, I'm going to go ahead and change this to y of s. Okay, here's 1. So we have s squared. We have this one, so it'll be a minus 2s. And then we'll have this one, so plus 5. Okay, y of 0 is 2. Y prime of 0 is 12. Okay, so now substituting those in, we'll have minus 2s, minus 12, and then with this 2 over here and the minus 2 times it, we'll have a plus 4. Okay, so we have y of s times s squared minus 2s plus 5, which does not factor, equal, we'll have 2s plus 8, and then minus 8 over s plus 1. Now we don't have a Laplace transform that just gives us s or 2s or 8, so we need to get a common denominator here, which would be s plus 1, or we could divide through on this side first and then see if we want to. That might be the easier way to go. So let's just do that. Instead of getting the common denominator then having to decompose it, we'll just go say this is y of s equal 2s over s squared minus 2s plus 5 plus 8 over s squared minus 2s plus 5 minus 8 over s plus 1 times s squared minus 2s plus 5. Okay, I'm going to go ahead and save us a little bit of time here. I'm going to go ahead and get a common denominator, which will be the s plus 1 times s squared minus 2s plus 5. So we're going to have 2s times s plus 1 plus 8 times s plus 1 minus 8. This ends up being 2s squared plus 10s, and then the 8's cancel. Now you'll recall from the last section we had this exact problem and we had to do a decomposition, and we found that this was equal to and to do this we had to get a complete square on this. And then because of this s minus 1, we saw that it was going to be a shift. we rewrote the top to be 3 times s minus 1, and we had to have a plus 8 to get the 5. Okay, so now we're ready. We've got that y of s is equal to that, so now take the inverse Laplace transform of both sides. And that's the inverse Laplace transform of, I'm going to go ahead and split this into two fractions, 3s minus 1 over s minus 1 squared plus 4 plus 8 times, oh, we actually split this, I didn't bring the 8 out, I actually just brought a 4 out because I knew I needed a 2 on the inside. 4 times the inverse Laplace transform of 2, that's the 8, s minus 1 squared plus 4, and then minus the inverse Laplace transform of 1 over s plus 1. Okay, so now bringing the 3 out, this is just 3 times, and we recognize that as the cosine of 2t. We had to do a shift where a was equal to 1, so that's e to the t. And then we have plus 4 times, again we got a shift of e to the t, and this one's a sine of 2t. And then minus just e to the minus t. So that was the y of t, and you can check it in the differential equation, you can check the initial conditions, but that should be the function that satisfies the differential equation. Let's look at another example. Same thing, we've got initial conditions both at 0, so we can apply Laplace transform to this differential equation. So taking the Laplace transform both sides, we have the Laplace transform of y double prime plus 4 times the Laplace transform of y prime minus 5 times the Laplace transform of y equal the Laplace transform of t e to the t. Okay, Laplace transform of y double prime we know is s squared times the Laplace transform of y minus s times y of 0 minus y prime of 0 okay, let's do the same thing for Laplace transform of y prime. So that'll be s times the Laplace transform of y minus just y of 0, and then minus 5 times the Laplace transform of y. That was the Laplace transform of y prime. And now, to get the Laplace transform of t e to the t, we can view it one of two ways. We can either look at it as a multiple of t times a function f, or we can do it as a exponential shift. So if we want to think of it as the exponential shift e to the t of whatever the value of the Laplace transform of t is, we know the Laplace transform of t is 1 over s squared, and instead of s squared though, we're going to replace it with s minus 1. You could also use the t times the e to the t and do the minus the derivative of the e to the t. The Laplace transform of the e to the t, which is 1 minus s. Okay, so we have 1 over s minus 1 squared. Okay, collect the L of y, which is really just the y of s, and I'm going to have an s squared plus a 4s minus a 5. Y of 0 is 1, so I'm going to replace y of 0 with 1 here and here, and then y prime of 0 is 0. So we're going to have minus s minus a 1 over here, wait, minus a 4 because it's 4 times that 1. Okay, so now solving for y of s, we get y of s is equal to s plus 4 plus 1 over s minus 1 squared. And then all of that divided by s squared plus 4s minus 5. Okay, let's get a common denominator of s minus 1 squared on the top. So that's s times s squared minus 2s plus 1 plus 4 times s squared minus 2s plus 1 plus 1. And then this will put this in the denominator. So we're going to have s cubed, this term. We'll have a minus 2s squared plus a 4s squared, so plus 2s squared. We'll have a plus s and a minus 8s, so it'll be a minus 7s, and then a plus 5. Let's see, and I think that might factor s squared. It'll be an s plus 5 and an s minus 1. Okay, so now the decomposition for this is over at the side here. I know that this will equal to some a over s minus 1 plus b, this is a repeated linear factor, b over s minus 1 squared, plus a c over s plus 5, and plus a d over s minus 1. And just to check, this is a lower degree than the denominator, which would be an s to the 4th. So now, multiplying through by the common denominator, I'm going to have s cubed plus 2s squared minus 7s plus 5 equal to a times s minus 1 times s plus 5 times s minus 1 plus b times s plus 5 times s minus 1 plus c times s minus 1 squared times, whoops, I lost it. Oh, that's an s minus 1 cubed. And notice that that was repeated that many times. Let me erase this. So when I factor that, I have an s minus 1 cubed here at the front. It's going to change the form. Okay, so now the form of the decomposition will be a over s minus 1 plus b over s minus 1 squared plus c over s minus 1 cubed plus d over s plus 5. Okay, so now multiply by the common denominator. We're going to plug in the values 1 and negative 5. And then we're going to have to pick some things. So probably 0 and maybe 2. I don't really want to expand that right side out, though I could if I had to. Okay. So when I plug in s equal 1, I'll have 1 plus 2 minus 7, 1 on the left. The first 2 and the last terms will be 0, and I get 6c. So c is 1/6. S is equal to negative 5. So that's negative 125 plus 2 times 25, so plus 50, plus 35, plus 5. So that's 90, so negative 35. Okay, and that's equal to, when I plug in negative 5, the first, the second, and the third terms are 0, and I'm going to get negative 6 cubed, so that'll be negative 216 d. So d would be 35 over 216. Okay, let's plug in 0. We'll get 5 on the left equal, we'll have 5a minus 5b plus 5c plus minus d. Okay, and plug in our c and d. We'll get those in just a minute. Let's go ahead and plug in 2 and get that equation. I'm going to have 8 plus 8, that's 16 minus 14, 2, 7, equal 7a plus 7b plus 7c plus d. Okay. Okay, so now let's take these equations, and I'm going to plug the c and the d that we already found into both of them. So I'm going to have 5 equal 5a minus 5b plus 5/6 minus 35 over 216. Okay, in the second equation, I'm going to have 7 equal to 7a plus 7b plus 7/6 plus 35 over 216. Okay, now I'm going to need to add all these numbers up. Okay, just cleaning up the first, here's my system, clean up the first equation a little bit, that I get that 5a plus minus 5b is equal to 935 over 216. And the second one becomes 7a plus 7b is equal to 1225 over 216. So I can reduce each of those down to a minus b is equal to 187 over 216, and the second one is a plus b equal to 175 over 216. So now simply adding and subtracting them will solve for the a and the b, and I end up getting the a is 181 over 216, and the b is negative 1 over 36. So those are my 4 values to decompose the equation, this polynomial. So I have over here then that the y of s is equal to the a, so 181 over 216 over s minus 1. The b is minus 1 over 36 over s minus 1 squared. The c is 1/6 over s minus 1 cubed, and then plus 35 over 216 over the s plus 5. So now take the inverse Laplace transform of both sides, which this will be just the y of t. Okay, so the inverse Laplace transform of this, it's 181 over 216 times the inverse Laplace transform of 1 over s minus 1 minus 1 over 36 inverse Laplace transform of 1 over s minus 1 squared plus 1/6 inverse Laplace transform of 1 over s minus 1 cubed, and then plus the 35 over, let me go ahead and get rid of this. Y of t then is 181 over 216 e to the t minus, now this is the 1 over s squared, which would be the Laplace transform of t, but because it's shifted, we'll have to have the exponential to the t times the t, which has the Laplace transform of the 1 over s squared, and then plus 1/6. Now this one is the 1 over s cubed, but let's remember that if you're trying to find the inverse Laplace transform of 1 over s minus 1 cubed, you know that the Laplace transform of t squared was 2 over s cubed. Okay, so we'd need a 2 on top, put a 1/2 out in front, and then we'll have that shift. So you've got the 1 over s cubed now with the 2, so that's going to be the 1/2, and then t squared shifted is e to the t. And then the last one is just 35 over 216 times e to the negative 5t. So one more pass. Y is equal to 181 over 216 e to the t minus 1 over 36 t e to the t plus 1/12 t squared e to the t plus 35 over 216 e to the minus 5t. Now you could have solved this one by using the methods that we did in chapter 4 and the method of undetermined coefficients, and you would have gotten these coefficients. Notice you've got that the roots of the auxiliary equation must have been repeated 3 times. It was probably the m minus 1 cubed because you've got it repeated 3 times. You had to add that extra t and t squared. And then this one. So there's more than one way to solve these, but when there's initial conditions, the Laplace transforms usually make the problem simpler. Okay, now we're going to look at a new function called the unit step function. It's defined to be u of t, and it's a piecewise function that has one point of discontinuity. You'll see that there's no value for the function when t is equal to 0. Okay, so this is going to allow us to look at Laplace transforms for functions that have a finite number of discontinuities. So looking at u of t, let's graph it. U of t's graph, the function's value will be 0 when t is less than 0. So u of t equal to 0 means we've got the horizontal line, y equal to 0. Doesn't have a value at 0, so I'll have a hole there. And then when t is bigger than 0, it has a value of 1. So that means it's going to jump up here to 1. Whoops, I need to draw a hole there as well. So put a hole up here at 1, and then it's going to have the value of 1 for all values of t greater than 0. Okay, so now let's look at the function u of t minus a. Now all we're doing is we're taking the function u of t and shifting it by replacing the t with t minus a. So if you remember, if you replace the independent variable with t minus a number, you're shifting that number to the right. So this will be moved over to a, okay, and it's going to have the value of 0 then to the left of 0, and it'll have the value of 1. Oops. For t values greater than a. So the definition of this u of t minus a would actually be u of t minus a will be 0 for t less than a, and it'll have the value of 1 for t greater than a. Okay, so now the last one here is m, just a constant m times u of t minus a. So it won't affect the value of 0. Okay, so our function m times u of t minus a will have the value of 0 for t less than a, and then we're multiplying the value for t greater than a, so 1 times the m. So it's going to have the value of m for t greater than a. So we'll still go over to a. We'll still have the value of 0 for values less than a, but then we'll go on up to some value m up here. No value at a, but it'll have the value of m. So it's just the line y equal to m for the t values bigger than a. Okay, so now this is called the rectangular window function. It's just a way to affect a value over a certain window of a certain interval. So we'll use the symbol capital pi. Okay, pi with an a comma b. It's a function of t. It's going to have the value of 0 for t less than a. It's going to have the value of 1 between a and b, and then it goes back down to the value of 0. So if I were graphing this, I'm going to have two different x values here, an a and a b. It's going to have the value of 0 for all values less than a. Between a and b, it's going to have the value of 1. And then for values of t bigger than b, we're going to be back down to 0. Okay, so that's what that window function looks like. Okay, so just in general, here's the graph right here. What that does for us is if you want to multiply that by a function, so if we start with some function f of t, so it's just defined on the entire, t axis, so from minus infinity to infinity. Multiplying that function t, f of t, by this window function pi just wipes out everything to the left of a and to the right of right of b, and just leaves the function's values in the middle. So you just see a window of that function from the interval from a to b. Okay, so now let's write a function that's a piecewise function with a finite number of discontinuities. Let's write it in terms of that window and then the step functions. Okay, so the window function, see, first I want the value of 3 for the values from 0 to 2. Now, it just says t less than 2, but we're assuming that the t is greater than or equal to 0 by the graph that they're showing us here. So we're going to have 3 times the window function from 0 to 2. And then we're going to add, now I can put of t. Then I'm going to add 1 times the window function from 2 to 5. So it's going to have the value of 1 in that one window. It's going to have the value of t in the window from 5 to 8. And then it's going to have the value of t squared over 10 for values greater than 8. So times the u of, because we can't use the window from 8 to infinity, so we're just going to use the t minus 8, that unit function. So that just says it's 0 before that. This portion of the equation would just have a value of 0 for t smaller than 8, and it'll have the value of t squared over 10 for t's greater than 8. Okay, so now if we wanted to write this, though, in terms of just the unit function, remember that the pi function is just u of, let me go back and show you, it's just u of t minus the a, so take the first number here and then minus the t of u of t minus b. Okay, so this is going to be u of t minus 0 minus u of t minus 2 this is equivalent to that, plus 1 times u of t minus 2 minus u of t minus 5 plus t times and then plus the t squared over 10 times u of t minus 8. So now I have it all in terms of unit step function. If I want to consolidate some of the terms, I only have one u of t minus 0, so I have 3 times u of t, which is t minus 0. I have a minus 3 times u of t minus 2, and then I have a 1 times u of t minus 2, so that's going to give me a minus 2 times u of t minus 2. I'm going to have a 1 minus 1 u of t minus 5, and I have a t times u of t minus 5. So I'm going to have a plus t minus 1 of u of t minus 5. And then I'm going to have a minus t times u of t minus 8, and then a t squared of u of t minus 8. So that'll give me a plus t squared over 10 minus t times u of t minus 8. So that's just written in terms of the unit step function. Okay, now we want to look at the Laplace transform of this unit step function. Okay, so by the definition, we know that u of t minus a has a value of 0 for t less than a, and we have a value of 1 for t bigger than a. So if I want the Laplace transform of u of t minus a, it's going to be the integral from 0 to a, e to the minus st times the function's value on that interval, which will be 0, plus the integral from a to infinity of e to the minus st times the function's value on the interval from a to infinity, which is 1. Okay, so this one's 0. This will be minus 1 over s, e to the minus st, and we evaluate that from a to infinity. So when you evaluate infinity, you get 0, and then minus a negative 1 over s, e to the minus as. So this comes out to be e to the minus as over s. So that's the Laplace transform of u of t minus a. So that means then that Laplace transform of u of t minus 5 would be e to the minus 5s over s. Okay, so we're going to use this. Okay, now let's look at a more general expression. What if we had a function times the u? Okay, so if we have a function times the u, I'm going to first start with a function with the same shift. So I'm going to look at f of t minus a times u of t minus a. So that's just going to be the integral. Again, u of t minus a will have a value of 0 from the interval from 0 to a. And so multiplying by f won't change that. So we'll have 0 on the interval from 0 to a. And then going from a to infinity, we've got e to the minus st times this function, because that'll be the value of this function on the interval from t greater than a. Okay, I'm going to make a substitution here. I'm going to use u equal to t minus a. So I know the du and the dt will be the same. And I know if the t is equal to a, that the u will be 0. And if t is infinity, the u will be infinity. So I'm just changing the limits of integration here. Okay, so u is t minus a means that t is actually u plus a. So now let me change this integral. So this one's 0. The second one will be the integral from 0 to infinity. E to the minus, the t is u plus a. And then we have f of u du. Now, I want functions of u here. Anything without a u I can pull out. So I've got an e to the minus su times an e to the minus sa. And I can pull this out since it doesn't depend on the variable of integration. It doesn't have a u's in it. So that's e to the minus as times the integral of e to the minus su f of u du. Now notice this, though, is just the Laplace transform where we're using the letter u for the constant of integration instead of t. So this will end up being just e to the minus as times whatever the Laplace transform is of the f. So I can use f of t or f of u, it doesn't matter. Okay, So what that means is that if we have a function times this unit step function where they both have the same shift, it's going to just end up being an exponential multiple of whatever the Laplace transform was of the f. Okay? Now remember back when we were looking at the Laplace transforms of functions that were exponential shifts, as times f of t. A t. So the function we were starting with was an exponential multiple of f of t. And we found that that was just the Laplace transform of the f of t shifted s minus a, or we wrote it as the capital F, whatever the Laplace transform of the little f was, and then just shifted a units. Okay, so this was looking at an exponential multiple relative to the t's, and the Laplace transform caused it to be a shift. Well, now this one is going backwards. We're looking at the functions of s, the things that are already Laplace transforms of something that are exponential multiples. And to go backwards, we're just going to have a shift of the function f. Whatever function had this Laplace transform will be shifted by t minus a units and then times the unit step function. So it's going to give us that piecewise function with that one discontinuity at a. Okay, so now the problem with using this, so this would help us find inverse Laplace transforms of things that look like this, that are the exponential shifts of some function that we do know the Laplace transform of. The problem is, if we were actually just trying to find Laplace transforms, it's very difficult working with a function that the f with a shift already incorporated, because most functions don't have a shift. For instance, if you wanted to look at f of t equal to sine of t, you don't have it written as f of t minus a. Now, if you had something like sine of t minus a, then that's already a shift. You could handle that one more easily. But if the function just starts with the sine of t, you're going to have to create and manipulate that to have a shift. So it makes it difficult to use. So what we want to do is we want to develop a formula to take the Laplace transform of a function that's times that unit step function more easily to get its Laplace transform. So we want to just have a function, g of t, not have to have the function have a shift built into it already. So to do that, all we're going to do is to let the function up here, I'm going to use the g of t to be the f of t minus a. Okay, so we have then that the Laplace transform of f of t minus a, u of t minus a, will be equal to e to the minus as times whatever the Laplace transform was of the f, the function f. Okay, well, if g of t is f of t minus a, that means that if you replace the t's here with t plus a, g of t plus a will be f of t plus a minus a, or just f of t. So f of t is just g of t plus a. So I'm just going to replace the f of t here with g of t plus a. So we have e to the minus as times the Laplace transform of g of the t plus a. Okay, so if you start with a function, just some g, not shifted the same amount, it's just going to give you a g of t plus a that you'll have to take the Laplace transform over on the right side. Okay, so now let's find Laplace transforms of some of these functions. Okay, so I've got a t squared times u of t minus a. So this is, it's not a function. If it had been in the form of t minus 1 squared so that it had the same exact shift as this, we would handle it differently. We would use our function f to be the t squared. But in this case, our g of t will be the t squared. Okay, so we're using the formula, the Laplace transform of g of t, u of t minus, now what's my a here? The a corresponds to that unit step function's value, so the a will be equal to 1. So this is what we want to take the Laplace transform of. And by the formula that we just created, this came out to be e to the minus as, e to the minus 1s times the Laplace transform of g of t plus 1 . Okay, so I'm just using the formula, but putting in the a equal to 1. Okay, so now let's find the Laplace transform of g of t plus 1. Well, we know g of t was t squared here, so that means g of t plus 1 is equal to t plus 1 squared, which expanded is t squared plus 2t plus 1. So I'm just going to replace that here. So this is e to the minus s times the Laplace transform of t squared plus 2t plus 1. Well, now we can just use the linearity property. This is e to the minus s times the Laplace transform of t squared plus e to the minus s. Well, I don't need to repeat that every time. E to the minus as times 2 times the Laplace transform of t plus the Laplace transform of 1. So e to the minus s times 2 factorial over s cubed plus 2 times 1 over s squared plus 1 times 1 over s. Okay, and so that would be the Laplace transform of t squared u of t minus 1. Okay, so now again we have a function, Laplace transform of cosine of t u of t minus pi. The first function, cosine, is not in terms of the same shift t minus pi. So we don't want to use that first formula. We'll again use the formula. Now in this case the a is pi. Okay, so the formula that I want to use then is the Laplace transform of g of t times u t minus pi is equal to e to the minus as, which pi s, times the Laplace transform of g of t plus pi. Okay, so that's the formula that we're going to follow. And in this case, our g of t is cosine of t. Okay, so that means that g of t plus pi is going to be cosine of t plus pi. Now, cosine of the sum of two angles, we had a formula back in trig. Cosine of a plus b is cosine a, cosine b, minus sine a, sine b. So this is equal to cosine of t, cosine of pi, minus sine of t, sine of pi. Well, sine of pi is 0. So this in cosine of pi, cosine of 0 is 1, cosine of pi is negative 1. So this is negative cosine of t. Okay, so now we know what g of t plus pi is minus cosine, so this becomes e to the minus pi s, and then the Laplace transform of minus cosine of t. Times the negative 1, I can pull the negative 1 out, and then the Laplace transform of cosine, which is just s now let's look at an inverse. Okay, so we have a formula. We know that if you have the Laplace transform of f of t minus a, u of t minus a, it was equal to e to the minus as times capital F of s. So the Laplace transform of whatever the function little f was over on this side. Okay, so that meant the inverse Laplace transform of e to the minus as f of s okay, so we need to look at whatever we're trying to find the inverse of. Okay, so look at this function and determine, compare it to this. We see that e to the minus as, it's e to the minus 2s. So for this problem, we see that the a is equal to 2. Okay, and so I'm going to rewrite this. This is going to be inverse Laplace transform of e to the minus 2s times the 1 over s squared. The f of s is the 1 over s squared. So what we need to find on this side is we need to find out what function had this Laplace transform. So if we find the inverse of 1 over s squared, which we know is just t, this is the f of t. So this function was the capital F of s, and this function is the little f of t that results. Well, over in the formula, though, we need f of t minus a, which the a is 2. So this will end up being f of t minus 2 times u of t minus 2. Okay, so now let's figure out what is f of t minus 2. Well, f of t was just equal to t because of this. So that means f of t minus 2 will be just t minus 2. Okay, so this is the function that would have the Laplace transform e to the minus 2s s squared. So when you see a function you're trying to get the inverse of that has this exponential multiple, pull it off, use it to determine the a, and then look at what's remaining to go back to the function that was multiplied by that unit step function with the shift. So now if I want to see what this function is, this is the statement of the function, but if I want to look at what it really is, this function is the value of 0 for t less than 2, and then it has the value of t minus 2 for t values bigger than 2. So we just have the function y equal t minus 2 for t is greater than 2. Okay, so that's your f of t function. Okay, let's look at one example all the way through. We've got a current I that's given, in a circuit that's governed by this initial value problem. So we have these initial conditions, and we have this differential equation. Okay, the function g on this right side is determined by this piecewise function that has a couple discontinuities in it. We want to find the current as a function of time. So we're looking for the I, the current I, and we have this differential equation containing the I. So the second derivative of I plus 4 times the I function itself is equal to that g. So the first step here is to rewrite the g of t using the unit step functions. So we know from what we just recently finished that g of t would be 1 times that window function from 0 to 1 plus negative 1 times the window function from 1 to 2 plus 0 times, the unit step function after that. So this is equal to 1 times the unit step function of t minus 0 minus unit step function of t minus 1 minus 1 times the unit step function of t minus 1 minus unit step function of t minus 2. So we're going to have 1 times the unit step function of t minus 0, or just t. We have a minus 1 times the unit step function and then we have another minus 1. So we'll have a minus 2 times the unit step function t minus 1, and then we'll have a plus 1 times the unit step function of t minus 2. Okay, so first is figuring out how to write g of t just as this streamlined function, just a function that we can work with and can find the Laplace transform of without having to go through the definition. Now we can also, since we're only dealing with t's greater than 0, this is just the function that would have a value of 1 for all t greater than 0. So this will just be equal to 1 minus 2 u of t minus 1 plus u of t minus 2. Okay, so now let's take the Laplace transform of both sides. I have the Laplace transform of I double prime plus 4 times the Laplace transform of I equal the Laplace transform of g of t. Okay, the Laplace transform of I double prime will be s squared times the Laplace transform of I minus s times I of 0 minus I prime of 0. Okay, that's the Laplace transform of second derivative. Now I'm going to replace the g of t with 1 minus 2u okay. And remember that we saw also that the Laplace transform of u of t minus a is equal to e to the minus as over s. Okay, now recall that the Laplace transform of u of t minus a is equal to e to the minus as over s. Okay, so we're going to use that when we get to this in just a minute. Okay. So I know that I of 0 is 0 and I prime of 0 is 0. So the left side then, if I factor out the L of a here and here, I'm going to have s squared plus 4 times the Laplace transform of I equal the Laplace transform of 1, which is 1 over s, minus 2 times the Laplace transform of u of t minus 1, which will be e to the minus 1s over s, plus the Laplace transform of u of t minus 2, which will be e to the minus 2s over s. Okay, so I've got Laplace transform of I is 1 over s times s squared plus 4 minus 2 times e to the minus s times 1 over s times s squared plus 4 plus e to the minus 2s times 1 over s times s squared plus 4. Okay, so notice here I have a common function that's occurring. I have a 1 over s times s squared plus 4 that appears 3 different times. So I'm going to just look at that function. To find I, I'm going to need the inverse Laplace transform of both sides. Okay, so I need to figure out what is the inverse Laplace transform of this, and to do that I'm going to have to decompose it. So using a partial fraction decomposition, I'm going to have 1 equal to a times s squared plus 4 plus s times bs plus c okay. The coefficient of the s squared would be 0. There's no term on the left side, so 0 is a plus b. There's no s term on the left, so that means the c has to be 0. And then the constant term for a is equal to 1. So that tells me that a is 1/4. For this to be true, the b has to be negative 1/4. So that decomposition then will be 1/4 times 1 over s plus The b is negative 1/4 times s. The c is 0, so it'll be times s over s squared plus 4. Okay, so if I call this function f of s, I've got f of s minus 2 e to the minus s f of s plus e to the minus 2s times f of s. Okay, and so I need to find the inverse Laplace transforms of this f of s. So the inverse of Laplace transform of I will just be simply I, and I need the inverse of this f of s minus 2 times e to the minus s of e to the minus s times that f of s plus so I'm writing them so that they resemble what we were looking at before. We saw previously that if we have an inverse of an exponential multiple, e to the as, it was just going to be whatever the little f is, shifted t minus a times the unit step function t minus a. So we need to find what the little f is, which corresponds to the inverse of this function, which this function is just this. So our little f of t is the inverse Laplace transform of 1/4 times 1 over s minus 1/4 times s over s squared plus 4, which is 1/4 times 1. The inverse of 1 over s is just 1, minus 1/4 times the inverse of this, which will be cosine of 2t. Okay, so that's your f of t. So just 1/4 cosine of 2t. Okay, but so this one will just be that function. The others, since this has an exponential multiple, I'm going to have to shift this function, t minus 1. Okay, so this has the a equal to 1, and this one has the a equal to 2. So we're going to have to do a shift of whatever the f of t came out to be by t minus 1 or t minus 2. Okay, so our I so that is this part, minus 2 times, now I need to take the function f here and shift it by t minus 1. So that's f of t minus 1 times the unit step function of t minus 1. Again, I'm just using this formula right here. And now plus, this one is going to result in a shift of the function f by t minus 2. So we're going to have plus 1/4 minus 1/4 cosine times the unit step function t minus 2. Okay, so this is the f of t minus 2, and this is the f of t minus 1. And you can clean this up a little bit algebraically, but or even write it as a piecewise function if you want to. But that is the current I relative to t. The graph of that function is the one here in the picture if you want to see how nice that current looks. Okay, a function is said to be periodic of period t if it repeats its values t units from where it started. Okay, so if it has a interval of length capital T where it repeats that same behavior. So one example of a function that you're familiar with that has a period is the sine function, and cosines also, right? The sine function has a period of 2 pi. Over this interval from 0 to 2 pi, it will repeat that same behavior for the whole number line. So we know that from 2 pi to 4 pi, it's going to repeat the same behavior, or from negative 2 pi to 0, it's going to repeat that same behavior. Okay, so that's a function. This one had a period. The period was equal to 2 pi. Okay, so just in general, a function with period t has f of t equal to f of t plus capital T. So the same function values t units from where it started. Okay, when you're specifying a periodic function, all you have to do is give the values over one period, since you know it repeats that same behavior everywhere else. So one specific periodic function that we're going to look at is called a square wave function. It has a value of 1 from 0 to 1 and negative 1 from 1 to 2. So you can see over an interval from 0 to 2 pi, the behavior that it has, so it's value of 1 here and negative 1 from 1 to 2, is repeated from 2 to 4. So it's 1 here, negative 1 here, or from negative 2 to 0, it's 1 here, negative 1 here, and it repeats that every 2 units. Okay, so now we're going to look at a special notation for a windowed version of the periodic function. Remember, the window restricts it to that one interval. So we're going to look at a rectangular window of width t and just look at the function's value over that one window and ignore all the other values down here. So we're just going to focus on this one set of values, and then we're going to look at the Laplace transform of that function and how it relates to the Laplace transform of the function from minus infinity to infinity. So we'll define this windowed function, little f of t, so we're looking at just that period of t. Okay, we want it to have the value of f of t from the 0 to t, and we're going to wipe it out everywhere else, so 0 to 0 everywhere else. So if we were writing that using the unit step function or the window function, we would say, well, that's the function value f of t over this window from 0 to t, or it's just going to be f of t, and remember, this notation just meant u of t minus 0 minus u of t minus t. So we can write it as this, just f of t u of t minus f of t u of t minus t. Okay, so now let's look at the Laplace transform. Okay, if f has a period of t and it's piecewise continuous on 0 to t, this will be the Laplace transform of the entire function. So that's the Laplace transform of f. So we would call this capital F of s, the Laplace transform of the little f, and this, the f with the little subscript t, is referring to the Laplace transform just over that interval from 0 to t. Now, since that function, the little f of t, had a value of 0 when t was bigger than the capital T, we don't have to worry about the integral from t to infinity. So we're just going to have this for the Laplace transform of this little function f of t. So this is the Laplace transform of the little f of t, that just one interval where it's defined. Okay, so now we want to see how are those two Laplace transforms, the capital F of t sub t and the f of t, related to each other. Well, if we go back and look at our function f and how it was defined, so we have that f of t is f of t u of t minus f of t u of t, t minus t. Okay? Now, recall f is periodic. So I'm going to rewrite the second f of t. I'm going to leave this one alone. This f of t, I'm just going to rewrite it as f of t minus capital T because it repeats the same values over that interval, for t units before that. Okay, so now let's take the Laplace transform of both sides. Okay, and this is the f sub t. Now, Laplace transform of f of t u of t, let's look at our formula that we had before. When we had a function f of t minus a, u of t minus a, it was e to the minus as times f of s. Okay, so f of the Laplace transform of the f of t Okay, so using this rule, where the a is 0, will be e to the 0 f of s. Now this is where we're taking the Laplace transform of the function f. And then minus, now the Laplace transform of this, we're going to have the a equal to t. So this will be e to the minus st times the f of s. Okay, now these were just the Laplace transform of the function f, not the f sub t. So now this is f of s. E to the 0, of course, is 1. So if we're trying to find the Laplace transform of s where it's a periodic function, we're going to have the Laplace transform of this t where we're just focusing on the Laplace transform of that function over the interval from 0 to t and divide by 1 minus e to the minus st. Okay, so I want the Laplace transform of this square wave function. So the first thing I need to do is to write that function. What does that square wave function look like? The square wave function, f of t, had a value of 1 from 0 to 1 and a value of negative 1 from 1 to 2. And the period was 2. So let's write it. I'm just going to write one period of it. It's going to have the value of 1. So I can write it as 1 times that windowed function plus negative 1 times the windowed function from 1 to 2. Or that's going to be 1 times u of t minus 0 minus u of t minus 1. And then minus 1 times u of t minus 1 minus u of t minus 2. So that's u of t minus 2 u of t minus 1 plus u of t minus 2. Okay, so the Laplace transform of this little f of t will be the Laplace transform of u of t minus 2u of t minus 1 plus u t minus 2. Laplace transform of u of t is simply just e to the 0 over s. Remember, a consequence of this, if we have the f function being 1, the Laplace transform of u of t minus a was equal to e to the minus as over s. Okay, so in this case, the a is 0. And then we'll have minus 2 times e to the a is 1, so it's e to the minus s over s plus a is 2, e to the minus 2s over s. that's the Laplace transform of the little f sub t, which we call the capital F of t of s. Okay, and this formula says that if we want to find the Laplace transform of the little f itself, it's just going to be this one's Laplace transform divided by 1 minus e to the minus s capital T, which was 2. Okay, and if I want to simplify that a little bit, if I notice that the numerator is the same thing as 1 minus e to the minus s squared, and then we'll go ahead and flip this down to the bottom, and then we'll factor this bottom. It's 1 minus e to the minus s and 1 plus e to the minus s. Okay, so then I can cancel one of those factors, which will leave me with 1 minus e to the minus s over s times 1 plus e to the minus s. Okay, and so that would be the Laplace transform. So if we just get the Laplace transform of one period, then we can just divide by that 1 minus e to the minus st to get it for the entire domain. Okay, let's look at a simple differential equation, y double prime plus y equal g of t. If we apply Laplace transforms to both sides, we'll have Laplace transform of y double prime plus Laplace transform of y equal the Laplace transform of g of t. Well, the Laplace transform of y double prime will be s squared times the Laplace transform of y minus s times y of 0 minus y prime of 0 using the notation that we've adopted, we would have then that s squared plus 1 times y of s. Now I'm going to assume that this differential equation had that y of 0 and y prime of 0 were both 0. Okay, so we get then s squared plus 1 times y of s equal to g of s. So that y of s is just 1 over s squared plus 1 times g of s. Okay. Next, to find the inverse Laplace transforms, in order to find the little y of t, we have to find the inverse of this product. Now, the inverse Laplace transform of a product is not just the inverse Laplace transform of 1 over s squared times the inverse Laplace transform of g of t. But it'd be nice if there was some expression that related those. The inverse of 1 over s squared plus 1 we know is sine of t. And we know the inverse Laplace transform of g of s is just the g of t. Now, the inverse is not the product, but it is the convolution of those two functions. And so now we want to look at what the convolution is and be able to get a simple expression in the cases where we end up with a product of two functions where we know what the inverse Laplace transform of each of them is separately. So we want to be able to get back to what that little y of t is, knowing that fact. Okay, so by definition, the convolution, if f and g are piecewise continuous functions, the convolution of f and g, and we denote it by this f star of g, is defined to be the integral from 0 to t, and this is f star g of t, and it'll be f evaluated at t minus v, g evaluated at v, dv. So we're integrating with respect to v, and we're evaluating the integral from 0 to t. Okay, so that's defined to be the convolution. So what we're going to do then is we're going to recognize that we have a situation like this where it's a product of two familiar functions that, they're Laplace transforms. And so we will know then that take the inverse Laplace transform of each of them separately and then just take the convolution. And we'll see that result in just a minute. So let's look a little closer at what is a convolution of two functions. So if I want to take two functions, t and t squared, t convoluted with t squared will be, okay, the function f and the function g is t squared. Okay, so if we take f of t equal to t, evaluate at t minus v, we're going to have t minus v times g of v, which will just be v squared, and we want to integrate that with respect to v. Okay, so integrating with respect to v, we need to multiply this out. So we'll have t v squared minus v cubed. Integrate with respect to v. So we'll have t v cubed over 3 minus v to the 4th over 4, and then evaluate from 0 to t. So we'll have t to the 4th over 3 minus t to the 4th over 4, and then minus 0, and that comes out to be t to the 4th over 12. So that's the convolution of t and t squared, and you can clearly see that that is not just the product of t and t squared. Okay, so we will use this result to get that the convolution of the two separate functions, and then we're going to use the integral to actually evaluate the expression. Okay, so some of the results, the properties of the convolution, is that if you took the convolution f star g, that's going to be equivalent to g star f. And you can prove that by just going back to the definition, setting it up as an integral, and doing a variable change. Okay. Also, f star, a sum. So f convoluted with the sum, g plus h, is just going to be f convoluted with g, and then summed with f convoluted with h. Okay, the convolution of f and g convoluted again with h is just f star g star h. Okay, so we have that associative property, we have a distributive type of property, and then we also know that f star 0 will just equal to 0. So we do have this multiplicative identity for this type of operation. Okay, so now the part that's going to be really useful is that if f and g are two piecewise functions of exponential order, meaning that they just have a Laplace transform, then if we use f of s to be the Laplace transform of f and g of s to be the Laplace transform of g, this is the result that's so important. The Laplace transform of convolution is just the product of the two separate Laplace transforms. Okay? So that means that if we're trying to do the inverse and we have two functions that we know they're Laplace transforms, the inverse of that product will just be the convolution of the two functions. So in the previous example that I showed you, that y of s equal to 1 over s squared plus 1 times the g of s, the inverse, which we know is just a little y of t that we're trying to get, the solution we're trying to get, will just be the convolution of, so we take the function that this is the Laplace transform, which is sine of t, and then the function that this has this Laplace transform is the little g of t, and that y will be whatever the convolution of that is. So then we can just set up the integral and figure out what the function would be. Okay, so if we wanted to get an expression for the y of t, we could set it up as an integral. It's going to be the integral of whatever the first function here is, sine evaluated at t minus v, times whatever the function g is. Now this is regular multiplication, evaluated at v, We're integrating with respect to v, and we'll integrate then from 0 to t. So that will be whatever your y of t is if we know what the g of v is, what that function was to begin with. Okay, now let's use the convolution theorem to solve this initial value problem. Okay, we're going to assume that the g of t is just a piecewise continuous function on the interval from 0 to infinity and is of exponential order. Okay, so first thing I'm going to do is take the Laplace transform of both sides. Okay, use the linearity property to break the left side up. That's just going to be the Laplace transform of the second derivative plus the Laplace transform of y. And then I'm going to call the Laplace transform of g of t just the function g of s. Okay, so now using the Laplace transform of a derivative, the Laplace transform of the second derivative will be s squared times y of s, or f of s, whatever you want to call it, minus s times y of 0, the initial condition, minus y prime of 0. So all of this is just the Laplace transform of the second derivative. And then I have plus the Laplace transform of y, which I'll just call that y of s, or f of s, whatever you want to call it, and then equal to g of s. Okay, so now I'm going to group the two terms that have y of s. So I have y of s times s squared plus 1. Now the y of 0 is just 0, so this term is 0. Y prime of 0 is 0, so this term is 0. So I have equal to just g of s, which leads me to y of s is 1 over s squared plus 1 times g of s. Now to find little y of t, the function whose Laplace transform is this, we now take the inverse Laplace transform of both sides. Okay, so we will get just little y of t. Now, I want the inverse Laplace transform of this product, and that is convolution. Okay, so these are the two functions that are the Laplace transform of some other functions. And recall that we know the Laplace transform of sine of t would be equal to 1 over s squared plus 1. So this function here is just the Laplace transform of sine of t. So when you have the inverse Laplace transform of a product of two functions, and you know each function, we know the Laplace transform of g of t is also the capital G of s, then this side becomes the function whose Laplace transform is 1 over s squared plus 1, which is sine of t, convoluted with the function whose Laplace transform is g of s. Okay, so we were able to take that product, and the inverse of it was, we could write it as a convolution. So now, we don't know what the g of t is. It's just some function that was piecewise continuous and of exponential order. But what we've just got now is we've got a representation for y of t. We know y of t will be the convolution of these two functions. So it's going to be the integral from 0 to t of sine evaluated at t minus v times g of v. So all I'm doing here is using the definition of a convolution. We know that f star g of t will be the integral from 0 to t of f of t minus v. Now v is just a variable of integration here. So that's all I used here when I applied it to this convolution, and that's what I get. So here's our variable, our integral representation for the function y for whatever piecewise continuous function of exponential order that we chose. Let's look at examples of where we might apply the convolution theorem. Okay, so we've set up a differential equation. We've taken the Laplace transform of both sides, and so we've got a function on the right side that's 1 over s squared plus 1 squared. So the next step to actually finding the y of t is to find the inverse Laplace transform of 1 over s squared plus 1 squared. Okay, well that's not one of the basic Laplace transforms that we're familiar with, but we would know if we had 1 over s squared plus 1, we could do that one. We know that one's just the sine of t. So we're going to rewrite this. This is the inverse of, I'm going to look at it as a product of two functions, 1 over s squared plus 1 times 1 over s squared plus 1. Okay, and we know that if we want the inverse of a product of two functions, Laplace transform, some f of s times g of s, we know the convolution theorem tells us that that is just the inverse of the f of s, which is the little f of t, convoluted with the g of t. Okay, so we just find the inverse of each one of those two functions separately. Inverse of f star, the inverse of the g. Okay, so we're going to break this problem up. This will be whatever the inverse of 1 over s squared plus 1 convoluted with the inverse of 1 over s squared plus 1. Okay, which we know this is just sine of t convoluted with sine of t. Okay, so now let's apply the definition. This is just sine, the integral from 0 to t of sine evaluated at t minus v times the second function, which is sine again, evaluated at v. Okay, now to integrate a product of two sines, we need to remember one of our identities from trig. Sine of a times sine of b is equal to 1/2 cosine of a minus b, and then minus cosine of a plus b. Okay, so applying that identity to this product, we'll have 1/2, which I'll put out in front, cosine of the difference of the two angles minus cosine of the sum of the two angles. Okay, so this will be cosine of t minus 2v, which I'm going to write that as negative 2v minus t. I'm doing that just to get the variable at the beginning and then make it positive. Okay, so now remember that another trig identity is that cosine of negative a is equal to just cosine of a. Remember, cosine's an even function. Okay, so I can just drop this negative here, and this just becomes cosine of 2v minus t minus cosine of t. Okay, so now let's integrate both terms. Cosine of 2v minus t will be sine, it'll actually be 1/2. If you do a u substitution, u would be 2v minus t. It'll be 1/2 sine of 2v minus t. And now cosine of t is just a constant relative to v, so this will just be minus v times cosine of t. And then we just want to evaluate that from 0 to t. Okay, plugging in t for all the v's. 2t minus t will just be sine of t, minus t times cosine of t, and then minus the 1/2, put in 0 for the v, and we'll have sine of negative t, and then minus 0 since 0 is plugged in for the v. So we've got 1/4 sine of t minus 1/2 t cosine of t. Now, recall that sine of negative t, sine is an odd function, so this is negative sine of t. So I can pull that negative out, and I will have a plus 1/4 sine of t. Okay, so we get then 1/2 sine of t minus 1/2 t cosine of t, or getting the common denominator, this will be sine of t minus t cosine of t all over 2. Okay, so let's look at another example. Okay, we want to solve this integral differential equation that has this integral involved in the expression of it for the derivative. We're looking for the little y of t. So now if you recognize that this expression is just a convolution, then we can change the form of it. So we're going to notice here that, okay, so instead of y of t, we have y of t minus v. So this would be the first function is y, convoluted with, now what function is this evaluated at v? So we could rewrite this as e to the minus 2x evaluated at v, and that would be, so this would be my g of x, and then my f of x is just the y of t, or y of x. So we evaluate the first function at t minus v, and we evaluate the second one at v, and so this is y convoluted with e to the minus 2t. Okay, so now let's take the Laplace transform of both sides. We'll have the Laplace transform of y prime equal the Laplace transform of 1 minus the Laplace transform of this convolution, which is the y, convoluted with e to the minus 2t. Okay, we know this is s times y of s minus y of 0 equal to 1 over s minus the Laplace transform of a convolution is just the product of the Laplace transforms. Okay, and this is just y of s. And we know the Laplace transform of e to the minus 2t is just 1 over s plus 2. And y of 0 we have up here is just 1. Okay, so now let's isolate the y of s. So we'll collect those on the same side. So we're going to have s plus 1 over s plus 2, y of s, equal to 1 plus 1 over s. So getting a common denominator here, I will have s squared plus 2s plus 1. So now notice that this is s plus 1 squared over s plus 2. Okay, so now isolating y of s, we get 1 divided by s plus 1 squared over s plus 2 will give us s plus 2 over s plus 1 squared. Okay, before I do that, let me go ahead and change this right side. Let me go ahead and get a common denominator over here as well. This will be s plus 1 over s. So then we'll just have one term to have to divide by, that s plus 1 squared over s plus 2. So we'll end up with just s plus 2 over s times s plus 1. Okay, now let's look at doing a partial fraction decomposition here. S plus 2 over s times s plus 1 will be a fraction with a over s plus some fraction b over s plus 1. Okay, so now if we substitute s equal to 0 into both sides, we'll get that 2 is equal to a. And if we plug in s equal negative 1 on both sides, we'll get that 1 is equal to negative b, so b is equal to 1, or negative 1. Okay, so this is equal to the a over s of 2 over s minus 1 over s plus 1. So now, take the inverse Laplace transform of both sides, and we get that y of t is equal to 2 times the inverse of 1 over s, which is simply 1, minus the inverse Laplace transform of 1 over s plus 1 is just e to the minus 1t. So our y of t is just 2 minus e to the minus t. Okay, so we've shown that Laplace transforms work well when you have initial value problems. So now let's look at a system of linear equations that have an initial value. So we have x prime and y prime in the equations, with x and y's possibly in the equations as well. So our two dependent variables that we're trying to solve for with this system is x of t and y of t. So you can see that t is the independent variable. So take the Laplace transform of both sides. The Laplace transform of x prime of t minus 2 times the Laplace transform of y of t is equal to 4 times the Laplace transform of just t. Okay, the second one, we have the Laplace transform of y prime plus 2 times the Laplace transform of y minus 4 times the Laplace transform of x of t is negative 4 times the Laplace transform of t minus 2 times the Laplace transform of 1. Okay, the Laplace transform of x prime will be s times x of s minus little x of 0 minus 2 times y of s is equal to 4 times the Laplace transform of t is 1 over s squared. The second one, s y of s minus y of 0 plus 2 times y of s minus 4 times x of s is minus 4 times 1 over s squared minus 2 times 1 over s. Okay, well, now we need to group the x of s's and the y of s's in both equations, line them up so that we can do elimination. So I have s times x of s minus 2 times y of s equal 4 over s squared. Now this x of 0 was 4, The y of 0 is -5. Okay, so I have a -4 on the left, so if I move it over to the right, it'll be a +4. The second equation, I have y of s in two places, okay, here and here. So I'm going to have s plus 2, well, that's y of s. And we have -4 times the x of s. Okay, I'll have equal to -4 over s squared, -2 over s, and then minus a 5, bringing this over. Okay, so now we're ready to do elimination. Either eliminate the x or eliminate the y. Okay, so now we need to decide which one we want to eliminate. We can eliminate one, then go back and eliminate the other and get the two answers that way. Or we can look up at the questions and realize that if we had x first, y will be really simple to solve for just by x prime of t minus 4 times t will equal to twice y of t. So y of t will just be this divided by 2. So let's first find x, and then we'll be able to get y easily from that. So we're going to eliminate the y. And we'll eliminate the y by multiplying the first equation through by s plus 2 and the second one through by 2. Okay, so I'm going to come up here. I'm going to have s times s plus 2 I'm going to get a common denominator on the right. Okay, the second equation. Okay, let's go and get a common denominator here as well. S squared and then we're multiplying through by 2. Okay, so now we're ready to add the equations. Okay, now we have a common denominator of s squared on the right side. Okay, now this coefficient here becomes s squared plus 2s minus 8. Okay, so now this expression on the right side, I could factor out an s squared out of both terms, which would cancel them with the bottom, so we're going to end up with just 4s minus 2. So this becomes x of s, 4s minus 2 over okay. Okay, I'm going to go ahead and write that in the form for the partial fraction decomposition. You know how to do that. This is equivalent to 3 over s plus 4, and then plus 1 over s minus 2. So then if we want to find the x of t, we just take the inverse of both of those. It'll be 3 times e to the minus 4t plus e to the 2t. Okay, so now let's go back and get our y of t. Okay, we know the y of t can be found by this formula, just solving the first one for y of t. So we have that y of t is 1/2 x prime of t minus 2t. X prime will be negative 12 e to the minus 4t plus 2 e to the 2t, and then minus 2t. So that's minus 6 e to the minus 4t plus e to the 2t minus 2t. Okay, so the solution to the system is both the x and the y functions of t.